It is not every day that I see a claim for a new formulation of quantum mechanics. That's exciting.
For almost 100 years, quantum mechanics has splintered physics into competing interpretations, each with a different consequence for reality. In this theolocution, Harvard's Jacob Barendis, co-director of the Graduate Studies Department, has developed a revolutionary framework called indivisible stochastic processes that suggest there is no fundamental wave function. He's joined with Scott Aaronson as they dispute other interpretations like many worlds and Bohm, as well as discussing, do quantum computers get their power from other universes? If so, why don't quantum computers provide speedups for all problems instead of just a specialized subclass? In Jacob's view, what actually gives quantum computers their power over classical computers is indivisibility, and that's because the class of indivisible processes is simply larger than the class of all the kinds of processes used by classical computers. My name's Kurt J. Mungle, and I use my background in mathematical physics to analyze various theories of everything. Can we finally understand quantum mechanics without invoking mysterious wave functions, or are we forever bound to a world of mathematical abstractions divorced from physical intuition? The audience is in for a huge treat. I've had a preview of the questions you have for one another, and I'm excited to be hosting you both. Thank you. Welcome, Scott Aaronson and Jacob Barendis.
Great to be here.
It's lovely to be here. Thanks for the invitation. Nice to see you, Scott.
Yeah, good to see you too, Jacob.
Does the benefit of quantum computing provide evidence for many worlds? Scott.
I would say that there is a philosophical argument that, for example, David Deutsch has made, right? That says that, and this was very closely related to why he invented the idea of quantum computing in the first place in the early 1980s. Right, that says, well, look, suppose that you use a quantum computer to factor a 2,000-digit number, right? And Deutsch said this very explicitly, in the 90s, right? Suppose you run Shor's factoring algorithm, and it factors the number, just vastly more efficiently than we think it can be done with any classical algorithm. And he says, if you don't believe that quantum reality is in some sense a vastly larger thing than classical reality, then where did the computation happen? Where was it done? Right. And so I think that does get at why quantum computing is so interesting to many of us in the first place, right? That it seems like this really, really hard to fake test that, yes, there is some kind of reality to these abstractions that we're talking about that do involve these vectors and this exponentially large space, right? But now I would say the philosophical part, the part where people can reasonably disagree with each other, is should you describe that in terms of parallel universes or not? Is that the right language to use for talking about this vast thing, right? The problem is that, what do we mean by something being a different universe, right? Usually, we mean that it is evolving independently from us, right? It is, its own separate thing. I mean, in the TV shows and the movies, there's always some portal or some wormhole or for by which you can visit the other universe. Because, if there weren't, then what would be the plot? Right. But somehow it is separated from our universe. Okay. But the trouble is, if it's separated, then for that very reason, we don't see the evidence of it. Like if we do a quantum computation, then, at the point when two branches, are really separated, then, we don't see the interference between them. We only see, our branch. And to the extent that you do see the interference, as you do in Shor's factoring algorithm, for example, or other algorithms for quantum computers, then you could say the very fact that these things could interfere means that they never really established separate identities as parallel universes at all. They were all just part of one giant interfering quantum mechanical blob. right? So I think that that's a philosophical objection. But I do agree that a quantum computation would be dramatic evidence that the state of the universe is this vastly bigger thing in some sense than what classical physics posits for it, right? And that is a huge deal. Now, I get annoyed when people will take the latest quantum computing experiment, like what Google did, with its Willow chip this past December, and they'll say, "Oh, this is new, evidence for the reality of parallel universe." It's like, no, no, it's not. It's just evidence that quantum computing works, like the theory said. And if you agreed with the philosophical argument that that can only be explained by many worlds, then you should have believed that way before this experiment, right? And if you didn't believe it, then you still shouldn't believe it. So it's not like these experiments are changing things that much. But there is this philosophical argument that I think is at the heart of why we care about quantum computing, why Deutsch invented it in the first place.
Briefly before you respond, Jacob, I want to know, well, what would David Deutsch say to your response about that the universes must be independent, so how would it manifest in this universe?
Oh, what would he say? I mean, Deutsch would say that you don't even need quantum computing to see the obvious truth of the many worlds interpretation. He would say that even the two slit experiment, from more than 100 years ago, where you see interference between two paths that a photon can take, even that clinches the case and can only be explained by the many worlds interpretation, and everyone else is just in denial about it. And then he would say, okay, but for those who are too dense to see that, building a quantum computer may help them psychologically. Right? It may, make it even more undeniable. But he thinks you don't even need it.
There's some very interesting history here, and Scott, I'm sure you're aware of this, but many of the people who are watching may not know. But Deutsch's development of quantum computing is really a fantastic example of how thinking philosophically and foundationally about physics in general and quantum mechanics in particular has borne tremendous fruit.
I
Um,
agree.
my understanding is the story is that Wheeler had him sit down at a dinner with Hugh Everett when Hugh Everett sort of came back out of retirement in the 70s.
Yeah, I can almost see the building where that happened.
Right. Yeah, yeah, yeah. And they sat next to each other.
Mhm.
And at the beginning, apparently Deutsch was skeptical or whatever, but by the end of the dinner, he was quite convinced. And then and just like Scott said, I mean, it's in the papers. It's kind of amazing, right? There's this foundational paper in quantum computing from 1985. It's quantum theory, the Church-Turing principle, and the universal quantum computer. And um, Deutsch is not shy about citing the Everett interpretation. It's like in the abstract, and throughout the paper, he's like, and this only makes sense under the Everett picture and the Everett. And he says very clearly that one of his motivations for developing quantum computing is to make just completely clear that the Everett approach has to be correct. What's interesting, and Scott, you mentioned this, and this is exactly on point. The sort of modern ideology that is dominant among people who think about and work on the Everett approach, and this is typified by books like David Wallace's 2012 book, The Emergent Multiverse, is that you really need decoherence, meaning the gradual disappearance of interference effects between the branches, in order for macro world branches and distinct universes to emerge. And that precisely doesn't happen in the middle of a good quantum computation.
Yes, that's what I was saying.
Right. Exactly. But my point is just that, like, this is what Scott's saying is really the standard way that most Everettians think about it. So the Everett approach doesn't really help you so much with quantum computing, because those other universes, they don't exist precisely in the case when they're being used, so to speak, for a good quantum computation.
Well,
And I'll just say a couple of things about this. One is there are a lot of situations in quantum mechanics where if you take seriously a particular philosophical perspective, at first glance, it may seem a little bit, helpful, revealing. Quantum computers in some circumstances can do things more efficiently than we believe is possible with classical computers. And the actual existence of multiple universes seems like maybe this is what gives these systems their advantage. But then on further reflection, it gets kind of strange, because if these universes are just really there, in some sense, whether in the microscopic case where, again, there's not agreement that we should be even thinking that way, or in the macroscopic case, you might think that you can get speedups in far more circumstances, that speedups would be far more generic. As Scott has at the top of his blog, right, his tagline, if you take one thing away from this blog, it's that quantum computers don't get speedups because they're trying out all the possibilities at once. And that's very confusing, because if you think those universes are there, you might just think you can get speedups all the time. It's actually kind of amazing that you only seem to be able to get speedups in very special circumstances. And so for me, this is almost evidence that we shouldn't be thinking that way. And Scott, you put this really beautifully. I forget when you said this, but you had this lovely quotation where you're like, these other universes are not quite as real as actual universes, and they're not quite as they live in some sort of intermediate regime between being real and being not real.
Boris Tsarelson, who said that. But yeah, I mean, I've been, banging my head against the pedagogical problem of how to explain quantum speed up for 25 years, right? And I like to say that, like, quantum computing is a weirder resource than any science fiction writer would have had the imagination to invent. Right. It's not just classical exponential parallelism, right? But, it's related. I mean, in order to explain it to people, usually we say, like, yes, you can create this superposition over exponentially many possible answers, but then you get only this tiny portal for observing something about it, right? You have to make a measurement. Measurement is a destructive thing in quantum mechanics. It collapses the state. And then your only hope of getting a speed up is to exploit the way that amplitudes in quantum mechanics, being complex numbers, work differently from the probabilities that we're used to, in particular that they can interfere with each other. So with every quantum algorithm, you are trying to choreograph a pattern of interference where the contributions to the amplitude of each wrong answer are canceling each other out. They're interfering destructively, whereas the contributions to the amplitude of the right answer are all adding up. They're constructively interfering, right? So that's not a thing that is, I mean, I can say that if you give me a few minutes, right? But that's not a thing that is easy to translate into any pithy English phrase that we had beforehand.
Right. Well, let me just say a couple of things about this. One is the use of branching tree-like graphical structures is not unique to quantum computing.
That's
if you're
right.
teaching a course in probability theory, we draw like outcome trees, probability trees, decision trees all the time to explain things. So, I mean, I completely grant that drawing trees of branches is a pedagogically useful exercise. But so I want to then jump on the point that you made, which is that the key to quantum computing is the ability to exploit the fact that these amplitudes are complex and that the different possibilities interfere, and you can use them to sort of cancel each other out. Interference is this very important property in getting quantum computing to work. So, and actually, I think that's kind of key, because if you think it's all about parallel universes, you might think you get speedups all the time. When you realize that it's actually requires this very delicate use of interference, then you realize the class of problems you're going to be able to get speedups for is actually not going to be be obvious and will require a lot of careful thought.
Right, we've been working on it for 30 years, trying to figure out what exactly is that class.
Right. Now, but go, yeah.
Sorry, I kind of like the analogy between the Everett interpretation and just, Darwinian evolution, where you have, these populations of species that can interfere with each other, namely reproduce sexually, right? But, that's only when the population remains, relatively close to each other in its DNA sequence, right? Once you have two isolated subpopulations that get far enough apart from each other, then they're never again going to merge. Right? Then they really have branched off into two separate branches, what, biologists would call two different species, and what in quantum mechanics we would just call separate Everett branches.
Yeah. It's a lovely metaphor and very helpful, especially pedagogically. Of course, then the question is, what is interference, and how do you explain interference to students?
Yes.
If you're not, and if these aren't really worlds, if they're not really macro worlds yet, because if they were well-defined macroscopic realities, they would have decohered, and then we can't do quantum computation with them. So, like, what are these things we're dealing with? And there's a kind of quietism that one practices. Let's just not talk about what they mean. Let's just draw them on paper and work with them. And I think we can do better. I mean, we don't have to do better if the goal for somebody is just to build better and more efficient quantum algorithms, to build quantum algorithms that can do more things. I think this is probably fine. But of course, we all come into thinking about quantum theory, quantum foundations, and philosophy of physics for a variety of reasons. And I think there are definitely a lot of people who would like a more physical picture that underlies this. And this is where my approach sort of comes in. And I'm happy to say a little bit for those who may be unfamiliar with my work and how it connects with this power of quantum computing. But let me
totally on board with wanting to understand the world, and not just predict the outcomes of experiments. So
right,
sure, and then we can talk about how to do that.
So Jacob, before you go on explaining your new formulation, I want to hear Scott Aronson's rendition of it.
Yes.
But first, before Scott Aronson, before you speak about Jacob's theory, in order for Jacob to say yes or no to you, I want you to tell the audience then, where do you think this efficiency comes from in quantum computing, or where does the interference occur? If it's not these many worlds, if you're not a believer in many worlds, then where do you personally, Scott, think the efficiencies come from?
I mean, a quantum speed up, really, if you think about it, just means classical slowdown, right? It means that our quantum computer, it can do something that cannot be done efficiently by any classical algorithm. Right. And so what it really means is just that of all of the different ways that you might have imagined that a classical computer could efficiently simulate this quantum computation, none of them work. Right. And so by its nature, there's not going to be just one explanation for that. Right. There might be a different explanation for every possible, way of simulating the thing classically. Right. It's quantum speed up is a negative statement at its core. Right. That none of the classical approaches work. And so I think that the exponential size of quantum states, when we write them down in the usual way, is part of the story. The entanglement of the qubits is part of the story. If there were an entanglement, then there would be a fast classical simulation because I could just keep track of the state of each particle separately in my classical computer. The interference is a huge part of the story because if it weren't for interference, then I could just use a classical computer with a random number generator and that would do the simulation, right? So it's really the combination of all of these elements, the, exponentially large Hilbert space, as we call it, the entanglement, the interference that is ruling out all of the different ways that you could simulate this thing efficiently with a classical computer. Actually, you even need more than that. There are examples of quantum computations, for example, what we call stabilizer quantum computations that have all of those elements, and yet still they can be efficiently simulated by a classical computer for another reason, right? So but you're, if you combine all of those elements, exponentially large Hilbert space, entanglement, interference, then at least there's a chance that you're going to evade any way of simulating what you're doing efficiently using a classical computer. And I think that's really what's going on.
Okay, now let's hear your recapitulation of Jacob's theory. And just for a background for the audience, Jacob has a theory or a formulation of quantum theory, a reformulation of quantum theory that gives an ontological account as to what's occurring. And it's been covered on Theories of Everything, this channel, at least 3 times. And I'll put each part on screen right now, and the links will be in the description. Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, kurtjaimungal.org.
Yeah, so it is not every day that I see a claim for a new formulation or interpretation of quantum mechanics. So, that's exciting. I mean, I tend to think that the basic options on the table, like Copenhagen or many worlds interpretation, Bohmian mechanics, have pretty much been around since the 1950s with minor rebrandings, combinations, elaborations since then. And Jacob is, saying he has something different. Actually, when I talked to physicists about this, they said, "Oh yeah, Jacob Barandis, isn't he the guy who has something that's kind of like Bohmian mechanics?" Uh, but I think it's not. I think I understand better than I did a month ago what is going on, and that it's not quite that. So basically, just to back up a little bit, I would say what Jacob wants is to give a new account that reproduces all of the empirical predictions of quantum mechanics. So he's not going to change the experimental predictions, right? That's what it means for something to be an interpretation or formulation instead of a new physical theory. Right. But he wants to do it with, using something that looks more like classical mechanics, where you have particles that will have, some objects that will have just definite classical configurations, such as just the positions of particles in three-dimensional space. Okay, and that puts him in a long tradition of people who have tried that, including Bohmian mechanics. Okay, but the difference is, in Bohmian mechanics, you retain the wave function, the quantum wave function in your ontology. So you still have this, gigantic wave of amplitudes, just like many worlds does. Okay, but then you use that wave to guide the particles along trajectories, right? So you have, let's say, particles that have some actual positions in three-dimensional space, and then those particles are guided. They're nudged around by the wave function in a way that's been precisely constructed to reproduce the predictions of standard quantum mechanics for what would you see when you measure those particles, right? Okay, so that's Bohmian mechanics. Now, Jacob, by contrast, is going to get rid of the wave function, to not have the wave function in his ontology, and he's not going to have the trajectories for the particles either, or not in general, anyway. Okay, what he's going to have is just you, like in Bohmian mechanics, you pick a basis, so you have what we call a preferred basis, which could mean like positions of particles in three-dimensional space or something like that. And then at any given time, he wants to say the particles, have a real position, or so, the system has a real configuration, a real state in that basis, even if you don't look. Okay, but now what he's going to give up on is trajectories for these configurations. Okay, so in general, we're not going to be allowed to ask, given that the particles were in this configuration at time t, what is the probability that they will be in this other configuration at time t plus one? Right. Or, sort of, we're only going to be allowed to ask that question, in the cases where it would, where it would normally make sense, right? When, in quantum mechanics, we would say that it's in superposition. Jacob would just say, well, you're allowed to ask at any, individual time, right? What is the probability that the particles are here or that they're there? But you're not allowed to ask, given that they're here now, what is the probability that they are there then? right? And so this is what he means in talking about indivisible stochastic dynamics. So he wants to reformulate, say, what in the standard picture would be the Schrodinger equation, that governs the evolution of the wave function, as a a differential equation that is governing the stochastic evolution of these, what we might call a hidden variable, except it's not really hidden, right? The classical positions of these particles. So he's going to give you an evolution equation for that, but it's not divisible. In the cases where in the standard account we would say that quantum interference is happening, you're not allowed to ask for transition probabilities. You're not allowed to ask for the whole path that is followed by these particles, or like, given that they're here now, then what's the chance that they're there then? It's just all one indivisible stochastic evolution. So that's my understanding of it, and now Jacob can tell me what I got wrong.
Thanks. Yeah. So let me just say a couple of things about this. The first is, there is a kind of a paradigm that we all work under. It's a paradigm that I grew up learning about when I took my university courses in quantum mechanics. I ended up doing a PhD in theoretical physics, and we used quantum theory all the time. I used a tremendous amount of quantum theory applied to fields, and so we learned quantum field theory. And so there's a certain way of thinking about quantum mechanics and thinking about how it's supposed to work, starting from the textbook axioms, the so-called Dirac, for Paul Dirac, von Neumann from John von Neumann axioms that you get from respectively 1930 and 1932. That's written in all the textbooks. And these axioms are, quick to summarize. Every quantum system has a Hilbert space. Every system has a quantum state defined in some mathematical terms, either as a state vector or a density, some object that lives in this Hilbert space. This object, when the system is evolving through time in a way where it's not mutually exchanging interactions or information with any other systems, evolves according to a rule called smooth unitary time evolution, which can usually be, for some systems, expressed as a differential equation. That's the Schrodinger equation. And then you have all these measurement axioms, all these axioms about what are the mathematical objects that represent the things that we can observe about the system? How do we get probabilities out of the theory for those measurement outcomes? That's called the Born rule. And then we're supposed to collapse the quantum state to reflect the result of the measurement and give robust, reliable predictions for subsequent measurements. Those are the standard picture. And this picture is built around the idea of the quantum state. There's this paradigm, I call it the wave function paradigm, that quantum theory begins by talking about wave functions or some suitable generalization of wave functions that live in Hilbert spaces. And then we're supposed to sort of figure out what we're supposed to do from there. When you start from this picture, it sounds very complicated to construct a different picture, because you start with all these Hilbert space ingredients. You're like, well, we've got a Hilbert space. Hilbert space is a kind of vector space. Vector spaces can be described using what are called different orthonormal bases. So what you have to do is you have to pick an orthonormal basis for some reason, and then from that orthonormal basis, you have to do this, and you have interference, and you have the Hilbert space, and you have the Schrodinger equation, which has to be translated back. I mean, when you start from this paradigm, it makes everything sound very complicated. And you see this all the time when you're talking about, different paradigms for a theory, that from maybe a newer paradigm, a newer paradigm can look very complicated when one attempts to express it in terms of an older one, or even very difficult to understand. And there's this whole theory, this whole story in the history and philosophy of science about the incommensurability of different paradigms. So let me just start from the beginning, okay?
I don't believe that paradigms really are incommensurable, but that's a separate discussion.
That's fine. I won't take a stand on this. I'm not ideological about this. I'm only saying that there is in the history and philosophy of science this idea that paradigms can be incommensurable. I won't take a stand on it. Yeah.
What I would say, Jacob, is that, if you say that this is, a new paradigm for quantum mechanics, and that, we shouldn't try to express it in terms of the old paradigm, then the task for you, the next task would be to explain, take all the successes of quantum mechanics, all the phenomena that we know about, including, Shor's algorithm, Grover's algorithm, quantum teleportation, and show how they have simpler explanations in terms of indivisible stochastic dynamics, right? And what you won't be allowed to do when you do that is say, well, just translate it back into the usual, ket notation, the usual Hilbert space picture, and then, just invoke this theorem that says that it has an equivalent representation in my picture. Because, if that's you're going to be your answer, then, you're telling me that in practice, I should just continue using the standard picture. Right. And I should continue to think in terms of it. Right. If you want me to switch to thinking in terms of a different picture, then you have to show me how all the specific successes of quantum mechanics that I care about actually are simpler to explain, present in terms of that new picture.
So let me say a couple of things about that
Yeah.
first, and then I'll
Yeah,
get
yeah.
to
Yeah.
So one of the things I'm going to do is explain what this approach is on its own terms. But of course, one of the important things about this approach is that it leads to an ability to reconstruct the standard axioms and the Hilbert space picture in its regime of validity, and say a little bit about why it has this sort of limited regime of validity and how one might extend that. But I'm not saying, to be super clear, right? I'm not saying that we should stop using the Hilbert space picture any more than, if you want to, study a problem in classical physics using the action angles formulation, or you want to do Hamilton-Jacobi theory, or you want to help yourself to canonical transformations or canonical perturbation theory, or one of a million other things that you might want to do, visualize trajectories in phase space, you're going to use the Hamiltonian phase space reformulation of classical physics. So if someone comes along and says, oh, you know about the Hamiltonian phase space formulation, you've got Q's representing positions or some generalization of positions, and P's representing some generalized notion of momenta, the so-called canonical momenta. And you have this phase space picture, and you've got the dynamics, the equations that describe how things evolve according to Hamilton's equations of motion. And you have these beautiful symmetries. You have this ability to do changes of canonical variables, these so-called canonical transformations that can scramble what the whole picture looks like. And someone comes along and says, actually, I think that there's a physical picture here. The thing you're describing is an object moving around, maybe it's stuck to a spring or on a pendulum, and the person says, well, okay, that's a useful picture, that's helpful, but will it help me do canonical perturbation theory? Will it help me do action angle variables? I would say, well, no, we have this beautiful Hamiltonian framework for doing that. You should use that still. Or another example is, we have general relativity. So general relativity, I've been teaching general relativity for 10 years, but when we do orbital calculations in sending spacecraft around, we still use the Newtonian paradigm. It's still very useful.
I understand the point, Jacob. I mean, but general relativity, at least, there is some class of situations where, this new language is better, right? So I think in this case, you at least have to show that there is some class of problems, of quantum mechanics problems, that are better treated using your new formulation than using the old one. Or else other people could justly say, then what is the point of learning it?
Or even can only be treated using your formulation.
Right. So, let me start with that. I want to get to explaining what it is, but let me just quickly jump to that. Okay. So, if what you're doing is, again, developing algorithms for quantum computing, I don't think there's no obvious sense in which this gives you the ability to do anything differently from what you would do in the old paradigm. The tools that we have are extremely good for these situations. You're studying tabletop kinds of systems where the Dirac-von Neumann axioms work really great, but those are not the only kinds of systems that physicists are interested in. So physicists are interested in applying quantum mechanics in astrophysical situations, to early universe cosmology, and people are trying to apply quantum mechanics in the context of quantum gravity. They're trying to do quantum mechanics applied to black holes. They're trying to do and now you're in situations where the Dirac-von Neumann axioms are very ambiguous about what you're supposed to be able to say. And this is where I sort of cut my teeth. I mean, again, I did my PhD here at Harvard in high energy theoretical physics. These are the kinds of problems that I studied, and I was often very confused about when we were legitimated in using the textbook version of quantum theory. And again, I wasn't the only one. I mean, we would routinely run into situations in which people would say, well, can we do this particular thing? Does this make sense? We have this sort of nonlinear dependence on this or that, and what's going on with black holes. And people were genuinely confused about how to apply quantum theory to these situations. But these are situations that are different from what you'd find in tabletop experiments. It'd be like saying, why do I need general relativity? On Earth, Newtonian gravity works fantastically. Well, there are systems that are beyond Earth where we may need a better theory because things get more extreme.
Let's agree that if you could say something new about quantum gravity, that would be great, right? No argument there. Now, if we think of you as, you are sort of hawking a new product at the Foundations of Quantum Mechanics Bazaar, right? Well, okay, the quantum gravity theorists are potential customers, right? I am also a potential customer, right? I am in the market for even just a reformulation of existing quantum mechanics that would help in coming up with new quantum algorithms, right? Or understanding for which problems quantum computers will give a speed up and for which they won't. If someone can give me that, that's great. I'll buy it.
Right. But so there's like a lot of things that one might want to do with reformulating quantum theory. One is, the existing approaches that we have, the existing, if you want, formulations, interpretations. Honestly, I know that the terms don't exactly mean the same thing, and there are some people who really like to be very precise about what they mean. But I'm happy to call this a formulation interpretation. That doesn't bother me.
Okay, but that at some point that might actually be the crux. Like, are you making a new ontological claim, or are you
Yes.
just giving a new mathematical reformulation?
Both. But both.
Okay.
So to be very clear
Okay.
for everybody, it's both.
Okay.
There's both an ontological statement about what is actually out there, and also sort of a new mathematical formulation. And to be clear, like when Paul Dirac introduced the path integral in his paper in 1932, Lagrangians and quantum mechanics, he was just curious how Lagrangians show up in in quantum mechanics, this classical idea of Lagrangians, because the theory at that point had been developed only in the Hamiltonian formulation. And it took 10 years before Richard Feynman came along and incorporated this idea into his PhD thesis. Then 6 more years in 1948 in Reviews of Modern Physics, and when he spelled out the idea for a broader physics audience. And even then, he said in the paper, there's nothing you can do here that you can't do using ordinary methods. It took decades for people to realize that there are situations in which you would never want to do things in the canonical Hamiltonian formulation. In particular, things like Yang-Mills theories, right? And the Standard Model is formulated in the Lagrangian path integral formulation for very good reasons. Sometimes ideas do take a while to come to fruition.
Sure.
And another good example is David Bohm's work. So decoherence goes back to David Bohm's work in 1951. He was doing trying to understand foundational questions of the measurement process in his textbook, Quantum Theory from 1951. And in chapter 22, he studies the measurement process. And famously in section 22.8, destruction of interference in the process of measurement, he introduces this idea of how decoherence works. And it takes decades for that eventually to become a major part of how we think about quantum computing, right? I mean, decoherence timescales are now a thing that people just talk about constantly. Things do take time, but you have to begin with a new idea. And I think it's just interesting when you have a new idea that isn't obviously wrong or inconsistent. So the first thing I'll just say is, like, certainly if there are any inconsistencies or problems with this new formulation, that's fair game. But if the only thing is to say, well, I don't know what to use it for yet, I think that's actually pretty good. We don't always know what to use things for initially.
In that case, let's delve into the idea. So I still want to know, like, did I get anything importantly wrong in my summary of what you were asserting?
So, okay. One, you made a comment earlier. Does this thing make any new predictions?
Yes.
I'm going to come to that point.
Okay.
Another, you talked about whether this thing has any trajectories in it. I'm going to come to that point again.
All right.
But broadly speaking, I think that if you're starting from the Hilbert space picture and trying to explain, like, backward how to go from the Hilbert space paradigm, if you want, to this paradigm, I think broadly speaking, your picture is right. But I think for people who are hearing this for the first time, it sounds very complicated. So let me just explain.
I mean, I'm just thinking of someone who already knows quantum mechanics and what is the quickest route to get them to understand what you were asserting.
Right.
Yeah.
But again, it'd be like starting with a Hamiltonian phase space formulation and saying we're going to pick a canonical frame.
What choice do we have? We have to meet people where they are.
Right. Absolutely.
Yeah.
Well, the choice is, for new people coming to quantum theory, right? Who aren't, But okay, so let me just start from the beginning.
Mm-hmm.
I listed all the Dirac-von Neumann axioms. They involve all these exotic ingredients. We're not going to do that. Here are the starting assumptions. Here are the axioms. The first is that a physical system has a configuration, and that configuration comes from some menu of configurations that we like to call, if it's a nice continuous set of possible configurations, a configuration space, not a physical space. And this is we call this the kinematical part of the theory, and it's very similar to what you would do in a classical theory. Classical theory, you begin by picking an appropriate set of or space of configurations that you want to use to model the system in question. If you want to study particles, you would pick arrangements of particles in space. If you want to do fields, you would consider configurations of field intensities localized at places in space. Or in a discrete system like in a computer, you would pick arrangements or patterns of on and off switches in the memory registers or whatever. So that's model dependent. You pick what you need for the model you want to do, and that's the first axiom. We just pick a set of configurations. Okay? The second is the dynamics. The dynamics means the dynamical laws, the mathematical laws that describe how configurations are supposed to change. And in physical theories up till now, under this sort of Laplacian paradigm, the idea is we have some kind of differential equation that takes our present configuration and then tells us later configurations in some smooth way, usually in the language of some giant differential equation. We don't do that. The new dynamical postulate is there's just this family of conditional probabilities, right? This collection of conditional probabilities of the form, given that the system is in such and such configuration at this conditioning time, this is the conditional probability the system will be in such and such configuration at a particular target time.
Conditioning time has to be a special time, right?
We'll talk about, that's what we'll talk about. So this is a sparse set of conditional probabilities.
Yeah.
They're not completely comprehensive. They're not, they don't exist for all conceivable, things you might, pick for target and conditioning times. In particular, the conditioning times are a little bit special. That's what makes these a sparse set of conditional probabilities. And because they're special, these processes are called indivisible processes. And indivisibility just means that there's like a failure of iterativeness. You can't just take some process over some amount of time and just act repeatedly with some map or rule that then gives you for each successive time, because that would assume that every single time is a time at which you can restart and condition on. If you give up that assumption, you have a simpler collection of conditional probabilities. These processes entered the research literature in 2020 in a preprint by Simon Mills and Kevin Modi in just sort of a throwaway comment in Figure 6 in their paper, which was a beautiful review article on classical and quantum stochastic processes that I highly recommend. It's on PRX Quantum. It's available for everyone. You can also get the archive version if you want, whatever. But and then ultimately it was published, like I said, in PRX Quantum. That was next year. So 2021. This is like a relatively new idea, hasn't been explored by people who work in statistics and in the theory of stochastic processes. These processes are not Markovian. So Markov processes are processes that have this nice iterative behavior, broadly speaking. I mean, it's a little bit more subtle than that. But even, when people have considered traditional non-Markovian processes, like in the textbooks, when people think about non-Markovian processes, they imagine these very, very intricate structures with these towers of higher and higher order conditional probabilities that are all different from each other. They get very, very complicated. They're very difficult to formulate and specify. And that's why people, when they can, typically try to write down Markov processes. These indivisible processes are even simpler than Markov processes. They fail to be Markovian, not because they're more complicated than Markov processes, but because they're actually simpler than them. They're so simple that people just kind of stumbled over them and didn't realize that they were that they existed. And I'm talking right now with people who work in the theory of stochastic processes, and they're like, "Oh, yeah, well, that's actually like a new idea." And new ideas are always exciting, right? I mean, when you realize there's something pretty simple that's been sitting around and people didn't notice it, there's new mathematics to be done. There's new ways to think about things. And remarkably, so you might have just thought, well, if there's this new kind of process that's simpler and more general than the processes we've been dealing with, can it do anything? Does it have any applications? And it turns out it appears to be exactly right to give you back quantum theory. So again, the two assumptions are configurations and configuration spaces, and the dynamical laws are these sparse conditional probabilities that generically will fail to be indivisible. Will generically fail to be divisible. They're called indivisible processes. And then there's a mathematical correspondence, a map, that's very analogous to the map between a classical Newtonian system and the Hamiltonian phase space formulation, which is this very mathematically abstract formulation with all these symmetries and all these calculational tools. And that correspondence is called the stochastic quantum correspondence, and it lets you go between the two pictures. So once you avail yourself of this map, you can just systematically reconstruct all the axioms. But now you know where they sort of come from, and you get these very beautiful ways to understand where some of the weirdnesses of quantum theory come from. So let me take, for example, the complex numbers. When you want to use this stochastic quantum correspondence, what you find generically is that it only works when the complex numbers are introduced at this step. So, or some algebraic structure that is algebraically equivalent or isomorphic to what we call the complex numbers. And that's actually really nice.
Close. Like you need square roots of negative numbers.
Yeah, absolutely. Right. But you could imagine, for example, representing complex numbers with like 2x2 matrices or something.
Sure.
But my point is, the stochastic process you start with doesn't have any complex numbers in it. It's written in the language of just ordinary old-fashioned probability theory, right? There's no Hilbert spaces, there's no it's just systems moving around, and the probabilities are old-fashioned probabilities that have all the usual rules of old-fashioned probabilities. And when you want to write it in this Hilbert space picture, what you find is that in most cases, the complex numbers are necessary to write down that description. And so this gives a very satisfying explanation of why we need the complex numbers in quantum theory.
I do think there's something nice that is going on there, like in the axiomatic reconstruction of quantum mechanics, which is another thing that people have, Lucian Hardy and many others have, Giulio Chiribella have tried for many years, which I would think of as a somewhat different game from interpretation of quantum mechanics.
Yes. I should say that those approaches, for example, Hardy's approach, right? He has this, and I recommend this to everybody who's listening because it's a beautiful paper. It's Quantum Mechanics from 5 Reasonable Axioms. But these approaches are explicitly instrumentalist. They're part of this larger idea called generalized probability theories, the other GPT, the original GPT, right. Which is just to treat quantum theory as kind of an instrumentalist device in which agents or observers do measurements on things. So these are not intended to be physical interpretations. So this, to be super clear, this is a very different kind of a picture. But let me go further, right? One question people have is like, why interference? Why linear? Where do these features come from? And interference is this very bizarre, as we were talking about earlier in this conversation, it's something about, if you take kind of a many worlds-ish kind of attitude, we've got different realities, but they're not really different realities yet because they're not macroscopic and they haven't decohered yet. And somehow they're complex numbers and they can cancel each other out, right? But like, what is going on physically? There's kind of no like clear physical picture here. But because you have this correspondence now between this Hilbert space story and this stochastic story, you can translate back and forth to get a physical picture. And if you translate interference back to this picture, what you find is that it's literally just the indivisibility. If you take a process and you start from some conditioning time and go to some target time, you'll get a statement about the conditional probabilities the system will end up where it does. If you, by hand, just demand that we can slice this process up and write down the kind of nearest approximate divisible counterpart to this process. You just divide it by fiat at this intermediate time and then try to treat it as a process with a division in the middle. You'll get the wrong answer. But what's fascinating is that when you compare the correct answer with indivisible dynamics to the wrong answer, you just subtract the predictions of the one from the other. The formula that pops out is exactly the formula for interference. So interference now has an interpretation. It's just, if you want to go to a formalism, not an indivisible formalism with laws that are sort of hard to apply, but you want to go to this nice, beautiful, clean, smooth Hilbert space formalism in which you can do time evolution in steps. You use unitary time evolution. It's nice and divisible. It looks Markovian. Then the cost you pay, the indivisibility doesn't go away. It manifests as this very abstract, very confusing kind of interference. But now the interference has like a physical meaning that it didn't have before.
I mean, that had better be the case, right?
Oh yeah, of course. It better be the case.
Reproduced quantum mechanics.
Absolutely. But let me get to
Yeah,
your question about
I think we're pretty much on the same page about what is being asserted,
right.
if we are, then, I can now explain, I think, very crisply, why, as an interpretation of quantum mechanics, why I am not buying this
Well,
product.
I have two points to make first that may change
All
your view
right,
on this.
all
So
right, all
let
right.
me get to these.
Okay, okay.
Okay. So uh, so the first thing before let me just say, because you're reconstructing the axioms of quantum theory, you don't have to go
Yeah.
through one at a time and check that every
Mhm.
single thing comes. Oh, you can, and some papers
Yeah,
do that.
yeah, yeah.
So you made a couple of things. One is this question about there are no trajectories.
Mhm,
I want to
yeah.
be a little more precise about this.
Okay.
The statement here is that there are. It's not that we're saying that there's no trajectories. What we're saying is the theory doesn't supply you with a precise description about what trajectories are taken. So, the system at any given moment, there is a probability distribution for the configuration of the system, and these probabilities, these distributions are where the system is changing. In some circumstances, you can make conditional probabilistic statements about where the system will be. In other cases, you can't. But this isn't to say that the trajectories aren't there, just that we don't have the tools from the theory to tell us what they're doing. Now, you could say this makes them unobservable, and then we can run into a discussion about should a theory have unobservables in it. But let me pass this over to Scott. Yeah.
Stand this. Are you committed to the existence of trajectories, even if you can't calculate their probabilities?
Yes.
You
Yes.
are.
Yes.
Okay, so you say that there really are trajectories.
Yeah, the system is really doing things.
It's just that your theory doesn't tell you their distribution.
Correct. Yep.
Okay.
Yep.
That is different from what I thought.
Excellent. Good. So
I thought that you were denying the existence of the trajectories.
No. There are trajectories.
You're saying,
the system is
okay.
following some path, but we just don't know what it is.
see.
If you had a God's
I
eye
see.
view and could see the entire universe unfolding, you'd see all these zany trajectories. You wouldn't need probabilities. You
I
wouldn't need
see.
quantum theory.
Right.
But we are limited,
it's-
epistemically limited beings.
But it's not just that your theory doesn't tell us the trajectories. It's that within the empirical framework of quantum mechanics, it would seem we cannot know them, even
Right.
in principle.
Yep.
Literally only God can know them.
That's right. I mean, I take the experiments. Experiments seem to indicate that when you do a measurement, you get one result.
Mhm.
The result is obtained probabilistically, and there's certain things that we cannot know, like trajectories of systems. And my approach just says, nature says that. Why don't we just believe nature?
As you know, on Theories of Everything, we delve into some of the most reality spiraling concepts from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, TOE, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.
Nature says that. Why don't we just believe nature? Okay.
Well, okay.
Yeah.
So then that is a very key difference from Bohmian mechanics, let's say, right? Where Bohmian mechanics will just say, among all the math, the choices that we could possibly make for distributions over trajectories that would reproduce the predictions of quantum mechanics, we are going to make this one particular choice. Right.
Right.
So Bohmian mechanics means, you're committing to a specific choice. And one of the central objections that I have always had to Bohmian mechanics is, well,
Why that
that
choice?
choice?
Yeah.
Why not 1,000 other equations that I could have also written down that would have been empirically indistinguishable from that one, right?
Agreed.
And so, you're saying, okay, well, there is some, distribution over trajectories, right? There is some, as there would be in
the
Bohmian
word
mechanics,
distribution,
and you're just
careful.
going to be completely agnostic about which.
Right. So to be clear, we're not providing a probability distribution over trajectories. That's kind of the thing.
You're not.
Yeah,
You're
right,
not.
exactly.
I understand that.
Excellent. Yeah.
Okay.
Yeah, but this isn't. I mean, so one objection one can always raise if you're not supplying individual trajectories, and
Yes.
I did a lot of early work in the modal interpretations. And the
Okay.
modal interpretations, the failure to provide trajectory information can lead to ontological instabilities that are very severe. Where like macroscopic systems can fluctuate between like cat alive, cat dead, cat alive again in ways that are sort of uncontrollable. So what you don't want is for the inability to specify trajectories to bleed into macroscopic systems. But what you can show is precisely because as systems get bigger and bigger, they have more and more and more of these division events that just arise from the interactions of the environment. That for macroscopic systems, you get a really nice, clean evolution. When you work in terms of collective variables and appropriately coarse-grained degrees of freedom, you find that macroscopic systems, they do move in very predictable ways, even though way down deep, their individual elementary particles or elementary constituents, whatever they are behaving in ways that can't be assigned within the theory specific trajectories. So it's very important that we close the gap between kind of the unpredictability of the trajectories for microscopic things and the emergence of nicer trajectories for big things. And this is something I'm very sensitive to, again, because of my early work in the modal interpretation. So I just wanted to say something quickly about the trajectories, and I'm glad we touched on that. The other thing I wanted to say was this question about, does this make different predictions? Yeah. So the Dirac-Von Neumann axioms are ambiguous about what should happen when you've got very large systems that you want to treat quantum mechanically, right? This is the heart of
systems include us.
They include us, but Schrodinger's cat, Wigner's friend experiment, right? And so there's just an ambiguity, and particular.
I mean, in some sense, as long as the cat or the friend or whatever is external to you, right? As long as you are willing to treat it as just a collection of atoms, even an enormous one, of evolving by Schrodinger evolution, then it is unambiguous what to do. But if you yourself are part of the system, I mean, I think that is when the empirical problem arises.
I mean, I think a way to put it, and I have this flow chart that maybe Kurt can attach, but I call it the Wigner's friend flow chart, and it's just basically like in the Wigner's friend thought experiment, which again, if people haven't heard about, the super quick summary is there's now two observers. Very important, there's now two. Hugh Everett, who first introduced it in the literature in his long form thesis in 1956, he phrased it as two observers. In the simplest case, one observer, Wigner, is outside of a box that is sufficiently sealed for the duration of the experiment that we can pretend that nothing leaks out of the box or goes in. And then Wigner's friend is a second observer inside this perfectly sealed box, along with some quantum system and some kind of superposition that this Wigner's friend is going to measure or do a measurement process on. And the question is, now that we have two observers, there's this ambiguity. Do we activate the collapse or the measurement axioms? Do we not activate them? Do we activate them for everybody or for nobody? And you can just construct a detailed... When I have this conversation with Wigner's friend, people tend to dodge and weave, right? I'll say one thing and then they'll go one way. I'll say that. But if you just draw a whole flowchart and just say, here's the flowchart, here are all of your options, you have to pick one. Yes or no to this, yes or no to that, yes or no to this, yes or no to that. And all of them end at some kind of either problem or they end at some kind of interpretive stance. If you believe that Wigner's friend on the inside, in fact, really does collapse the quantum state by this measurement, then you run into the measurement problem, right? Head on into what counts as measurements, what doesn't count as measurements. If you believe that collapse happened, but it wasn't because of the measurement, then you're talking about a dynamical collapse or some other theory about why collapses happen. If you don't believe that the overall wave function is collapsed, then either Wigner's friend did in fact have a result. There was, in fact, a result despite the fact that it's not reflected in the overall wave function, and that is by definition a hidden variables approach. And a lot of physicists implicitly take this approach if they don't want to be Mennewalders. They're like, well, we just have to be perspectival. There are different perspectives. Wigner on the outside assigns one wave function. Wigner's friend on the inside has a definite result, but this is literally a hidden variables approach. Or you deny that there was, in fact, a definite outcome, and you're either embracing that more than one outcome has somehow happened, and that's kind of a many worlds type ontology, or that nothing happened, that without that Wigner's from the inside somehow didn't yield anything at all, and then you're embracing some kind of anti-realism, which is going to be radically self-undermining. And those are your options. You have to pick something, and I know that you can sort of try to not, but it's just sort of steering you right there. I am explicitly embracing the option that the overall well, on the Hilbert space side, we would say the overall wave function. And the stochastic side, we would just say that there's just this ongoing indivisible stochastic process happening that isn't broken. That's what's going on for the overall system. And at the same time, Wigner's friend did have a definite result. So you can think of this, if you want, as a hidden variables approach, although, as Scott pointed out, these variables are certainly not hidden to Wigner's friend, and they're not extra or additional variables because the wave function is not a physical object. These variables are the only things there are. So I'm explicitly embracing that part of the flowchart. And that makes a prediction different from the Dirac-von Neumann axioms, which just either run into the measurement problem or are ambiguous about what's supposed to come out.
For the benefit of listeners, I think we should say that the trouble with using the Wigner's friend thought experiment to get predictions is that at the end of the experiment, the Wigner's friend doesn't actually have a memory of what happened, which we could use to test this prediction. Right. So like by the time it comes to, we ask the friend at the end, what did you experience? Right. And then we write it down and we publish it in a journal. Right. Then we all know how to do the calculation for what the friend is going to say. Right. Is just going to follow the usual Born rule of quantum mechanics, unless, there's some dynamical collapse thing going on or something of that kind. Right. But otherwise, you're just going to see the same, quantum mechanics that we've known for 100 years, right? If there's any empirical difference, it can only be in what Wigner's friend is experiencing while the experiment is underway. But, once it's done, they've got no memory of it. That's the problem.
Just for the benefits of the viewer, I'm going to place the image that Jacob was referencing on screen. And then I also want to bring up that I asked you, Jacob, the last time, hey, what's the difference between Wigner's friend experiment or thought experiment and the Schrodinger's cat, except the cat is now a friend?
Yeah, they're basically the same thing. It's just a question of like, is this are we worried about just a large system being placed in superposition? Are we worried about the fact that it's alive, or are we worried about the fact that it's conscious and that like in some sense we could be it?
Yeah, essentially, it's just that cats can't usually report experimental findings.
Right. You can just sort of heighten the dramatic stakes by going from like just a really large object to a cat that's meowing, to a friend who you could actually talk to.
A cat that can take data and report it would be Wigner's friend, basically.
Someone wrote a hilarious comment which said, "No, Kurt, you're wrong because cats are never a person's friend."
Well, that's clearly wrong.
I don't think
I think we can agree on that.
I don't think that's true
or
at
that
all,
cats
then.
never treat humans as their friend, something like that.
Well, I mean, that's cats
can be friendly, but on their own terms. So that's the difference from dogs.
Right. But let me just quickly say about this comment about we all know what would happen. Actually, we don't know what would happen. And the reason I say that is, according to the Dirac-von Neumann axioms, if you read the axioms one way, then there in fact is overall unitary evolution. The whole apparatus evolves. As far as Wigner on the outside is concerned, there's no loss of coherence, and we can do in principle interference experiments, or even do a reverse unitary and reverse the system to where it started. But the Dirac-von Neumann axioms, they say that when a measurement is done, then things collapse. And if you take that seriously, then you can't do those operations. You can't do interference experiments on Wigner's on the box. You can't undo the procedure unitarily. And so this is the ambiguity. And I think what you're basically saying is, which is what most physicists do, is we're going to resolve that ambiguity in favor of maintaining unitary evolution. But that, strictly speaking, goes outside the Dirac-von Neumann axiom. So when a physicist says this to me, they're like, we don't need all this philosophy. We don't need quantum foundations, but in the Wigner's friend thought experiment, we're going to take this prong of the fork. They're explicitly saying that they're now outside of the boundaries of the Dirac-von Neumann axioms. They're making a claim that goes beyond the axioms. And then as far as I'm concerned, they're already halfway there, right? Like once you agree that the Dirac-von axioms are ambiguous or incomplete or insufficient for this experiment, well, then you're on my playing field. This is now we just have to give an account that's consistent of when we're allowed to do this and when we're not supposed to do this, or justify it. If the Dirac-von Neumann axioms are not available anymore, if we've gone beyond them, then we need new axioms, right? Because if you're outside of your axiomatic framework, you're just flying around in the void. You need somewhere else to stand. And all I'm saying is that we should have another set of axioms that would allow us legitimately and honestly to be able to make the statement that you just made.
So the audience is here and has been watching since the beginning and knows Scott is in the market. Scott is a working
Yes.
quantum mechanic
Yes.
who actually wants to buy from you, Jacob. He just wants to make sure that you have something that's worth buying, but he
Yeah.
wants it. So now Scott probably has some objections like, I would buy from you, Jacob, but A, B, and C. So what is it?
Yeah. So at some point in this podcast, I did want to say, why I think I am not currently buying this product. I might revisit it in the future. If it, and I'm very happy for Jacob to hawk this product to other people, but I can explain why you have not closed the sale with me today. Okay. And the reason is, if you are telling me that, there are, particles that, have real positions in space. And now you're also telling me that those particles have trajectories, right? But the trajectories are unknowable by us, right? You can only from quantum theory, you can only get this indivisible stochastic dynamics, right? That just sort of tells you, we're not allowed to ask, right? And so, for example, if I am Wigner's friend in the experiment, I cannot use this to predict, given that I am having this one experience at one time, then what is the probability that I will have a different experience 2 seconds from now? Right. I can't actually use it for that. It is unknowable but by me. Right. Well, guess what? That's what standard quantum mechanics told me. It told me it is unknowable by us, and I feel like at that point, I might as well just say that, what is knowable, what is within the ambit of physics to talk about is the wave function, which is what most views of quantum mechanics have been saying for 100 years, right? Like I haven't sufficiently improved over that. Right. For me, to say, for let's say in the double slit experiment, to say that, we can improve over, the just having a wave function where there's some amplitude for the photon to go through the first slit and some amplitude to go through the second slit. It means saying something like, okay, well, really the photon goes through one slit or the other slit, and I can tell you the path that the photon will take. Right, which is exactly what the Bohmians, claim to do. Right. If you're not going to say that, if you're just going to tell me, well, these indivisible stochastic dynamics give you the probability distribution over where you'll find the photon if you were to measure it at any intermediate time, right? Uh, 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 but if you don't measure it at the intermediate times, then it could be jumping around in some way that's only known to God. Well, I feel like, that's what standard quantum mechanics already told me, right? It already told me how to calculate the probabilities if I measure the photon at any specific time. And it told me that, if I don't make the measurement, then I don't get transition probabilities, right? So, just sort of metaphysically asserting that, there is this basis in which transition probabilities exist. And I can't know what those transition probabilities are. I can't know what the distribution over trajectories is. It just feels like an ontological commitment that is not paying rent for me. It is not sufficiently improving. I have a very strong belief. Like I do want to know what is really out there in the world. I am not an instrumentalist, right? But I want to fit my ontology as tightly as possible to what is actually observable or what is at least in principle observable. Right. Because I think the history of physics has given us so many examples where people confuse themselves by, let's say, reifying, things like the in general relativity, the coordinates, right, or the choice of gauge, and get right the things that don't actually make a physical difference, the global phase of the wave function. Right. And again, the right answer has been try to just cut out from your ontology things that are not observable even in principle, right? Have an ontology that is as, you know, tightly fit as possible to the set of all things that could in principle be observed. And whatever my reservations about the many worlds interpretation, and I do have reservations about it, but at least it tries very hard to do that. Right? It tries to say, look, the wave function is the encoding of everything in principle that's observable. So that's what we're going to take as our ontology, full stop. It is the wave function. And if we don't have to add anything additional to that, then we're not going to do that. Um, and Bohmian mechanics, of course, does try to add something additional, and it tells a very specific story, right? And of course, one can then object, well, why that story as opposed to 100 other stories? But at least it is a story, right? At least, there's a clear story that we can stare at and poke at and see if we like it, right? Now I feel like we are adding additional ontology without adding a story that goes with it in Jacob's view. And like that is a thing that you can do. But I don't see I'm going to get something from that is worth the price of admission. At least not for me, not right now. But I would say go in peace. If this helps for quantum gravity, that would be awesome, and that would certainly be one reason to take another look. If this gives new insight into quantum information protocols or quantum computing, that would certainly be another reason for me personally to take a look. And I feel like, until something like that happens, that I'm just going to say, I pass on this product, go in peace.
So I have a couple of points to make about about that. So
Yeah.
just first, a couple of like technical asides.
Sure.
At one point, you said, "Well, Wigner's friend on the inside knows the result, but then doesn't know what he's going to be doing in 2 seconds from now." That's actually not right because the measurement that Wigner's friend does generates a division event, and the division event is a place at which you can then make conditional probabilistic predictions from that moment.
So the scenario that I had in mind implicitly is that let's say Wigner's friend is in a superposition of two mental states, and then we do a Hadamard operation on that. So we do some interfering operation, or in your terms, some indivisible operation that maps us from one superposition to a different one. And then the issue is that, in normal quantum mechanics, we would not get transition probabilities. That's the scenario that I was.
That's fine, right? Exactly.
Yeah.
But for Wigner or you or anyone doing measurements like regular life, you're gonna be able to make those predictions, and those comport with what we see. Okay, so
I understand that. I mean, let me
get to a
because
couple,
real life is pretty decoherent.
Yeah, exactly. But let me now get to a couple of the items you brought up. And let me just say, first of all, before we even get started, not everybody has to agree that this is the way to go. I'm not selling this to you personally, Scott, although it would be lovely if you liked it. We're all looking for different things, right? Like I said. And, when you're teaching quantum mechanics and we just sort of snow over students, we stupefy them by saying, here are the axioms. And the students look on, gawking, and they're just like Hilbert spaces, linear algebra, density matrices, self-adjoint linear operators, POVMs, and, you render them in a state where they can't even be able to ask questions about why.
I only introduce those things as needed, but of course I'm also in the market for better pedagogical ways of teaching quantum information, to students. I would love that, but it sounds like even if I believed in your, philosophical commitments, it sounds to me like I would still have to teach the students about Hilbert spaces and unitary transformations and all those things because how else are they going to, do the calculations?
Agreed. But there's a difference between saying I've got forces in Newtonian mechanics that push on things, and then through like a sequence of mathematical transformations, I can turn that into the Hamilton equations of motion or the principle of least action. And then, by contrast, showing up the first day and just saying Hamilton's equations of motion or principle of least action with Hamiltonians and Lagrange. I mean, there's a total pedagogical difference there. But okay, let me put all that aside. So, let me add one other point which I think is important. This old joke, right? That these two campers and they hear a bear.
Yeah.
And one of them starts running and the other one starts putting, their shoes on. And the person's like, what are you doing? You can't outrun a bear. And the person's like, I just have to outrun you. I'm not proposing here that this interpretation or formulation is going to satisfy everybody. And I'm not saying that it's necessarily the final word. I mean, we don't even know if quantum theory is the final word, right? I mean, if we're trying to develop a theory of quantum gravity, it's possible that quantum theory will have to be modified in some even more profound way that is specified by this approach. But the question is this at least an improvement over the other interpretive or formulations that we have? And I have a clear set of reasons why I think that is the case. So if someone is coming to me and saying, we've got enough interpretations already, why do we need another one? I'm just going to sit back and sit on many worlds, or I'm going to recline on Bohmian mechanics, or I'm going to recline on Copenhagen or whatever. What I'm telling you is that those are not true safe harbors, right? They're giving us a false sense of security. Here is a list of criteria that I would argue are required of any good theoretical framework in physics or formulation, and certainly for quantum mechanics, even apart from any aesthetic judgments or preferences. One is the thing has to be empirically adequate, right? It has to make predictions. The predictions have to agree with what we're seeing. That's just the first item for all the kinds of systems that we're interested in quantum mechanics. So empirical adequacy is the first. The second is it shouldn't be vague. If someone asks you a question and they just sort of dodge and weave and they're vague and, I don't know what we could say, but we kind of know it when we see it. We'll use our expert intuition. Like that's vagueness. The third is it shouldn't be unambiguous at making predictions for certain kinds of systems that, while may be practically difficult to study, in principle one could study. And this is again like macroscopic type systems like in the Wigner's friend setup. There should be at least a schematic in principle story to be told about how the classical world is supposed to emerge. It doesn't have to, I mean, obviously getting all the precise details is going to be very difficult. It's very difficult to, do all the details and explain how even classically, classical deterministic kinds of dynamics emerge from classical statistical mechanics, but there's at least like a schematic story about how that's supposed to work. And then the final thing is it shouldn't depend on a long list of what I call SMHs, speculative metaphysical hypotheses, or ad hoc extra empirical axioms in order to get it off the ground, a long list of epicycles. Like those are the things that I think we should reasonably require. And my view is that none of the interpretive approaches we have meet those minimal requirements. Right. And I can explain in detail why each of them doesn't. Bohmian mechanics has proved very, very hard to generalize beyond systems of fixed numbers of finitely many non-relativistic particles. So it's proved very difficult to use it to understand how quantum field theories are supposed to work. And the Standard Model, our best theory of the fundamental interactions, is written in terms of quantum field theory. In particular, Bohmian mechanics has a great deal of difficulty handling what are called fermionic quantum field theories, which don't have traditional configuration spaces of the kind that Bohmian mechanics would want to help itself to. Bohmian mechanics
Make up a new evolution rule, even if it's a stochastic one.
People,
you may have to pick a preferred reference frame or things like that.
That's what people do.
Well, look, here's maybe the core of my objection, right? That like I feel like Bohmian mechanics has all these problems because it tries to make a concrete commitment, right? And you're avoiding that just by not making a commitment to what are the trajectories. Right? Like as soon as you made that commitment, then you would have the same problems as Bohmian mechanics.
Yeah, you're right. Bohmian mechanics attempts to write down like very carefully written down, complicated, some would argue gerrymandered stochastic dynamics in these sorts of situations. This is the work of people like Shelley Goldstein and so forth who've tried to generalize this. When they need preferred reference frames. It turns out to be super duper complicated, and it looks very sort of frankly ham-fisted, right?
Yeah, I agree. They
have a clear target they're trying to replicate it.
That is not the product for me either, right? But so, I mean, look, Jacob, once you have told me now that you are committed to the existence of trajectories, even if we can't, know their distribution in principle, now actually your view sounds more similar to Bohmian mechanics than I thought going into this conversation, but it feels to me like Bohm minus. It is Bohm, except you're taking away the specific commitment about the guiding equation. And you're saying, who knows? Which, yes, you can do that. But, I even would have known before that was an interpretive option that was on the table, even though I wouldn't have phrased it in terms of indivisible stochastic dynamics.
Yeah. So let me just say, earlier on when you mentioned Bohmian mechanics, you talked about the physicality of the pilot wave. I should just note that when Bohm introduced Bohmian mechanics in 1952, he did take the pilot wave to be a physical object. He's very clear about that in his papers. But and there are still Bohmians who take that view. But I mentioned Shelley Goldstein, but Goldstein, Durr, Zangi, they've embraced since the 90s a view of Bohmian mechanics in which the wave function is not a physical object, but it's an expression of what's called nomology. It's a law-like expression, which actually brings quantum mechanics in some ways back to its roots. When Schrödinger introduced his undulatory or wave mechanics picture, he built his wave function out of Hamilton's principal functions, which are an expression of a certain kind of law-like thing. Basically, he took the Hamilton-Jacobi function, stuck it into the phase of a function. He called that his wave function. And so in a way that's sort of bringing it full circle. There is a sense in which what I'm doing, like the nearest, the least squares approximation of what I'm doing from existing interpretive frameworks is that it's most similar in some ways to this nomological view of Bohmian mechanics, but without the preferred foliation of space-time, without a particularly gerrymandered set of laws.
Right.
The laws are simpler.
Without the guiding equation, with
right.
specific commitment of what are
That's
the trajectories, which to me was the sort of distinctive feature of Bohmian mechanics, that, you make this commitment. You're just taking that out and saying there are some trajectories. It is unknowable what they are. Okay, fine.
Yeah. And what this gives you is simpler laws and also greater generalizability, because now you can apply this to basically any kind of a system. So the ability to generalize is useful, but let me actually say something else here. So you have this paper from 2004, Is Quantum Theory an Island in Theory Space? But in this paper, you're like, could we have modified any of the features of quantum theory to look for a different theory? Could we have, for example, written down a quantum theory that didn't use the complex numbers? Could we do a quantum theory where we modify this feature or that feature or this feature? And what I love about that paper is, you're not taking for granted that nature has bequeathed unto us this particular. You're imagining maybe there could be a different kind of a theory out there, and it's worth trying to see where we can generalize quantum theory in anticipation of the possibility that maybe we'll have an experimental result that will require a generalization of quantum theory.
Sure.
There are only so many things you can do when you begin from the Hilbert space formulation. If you do too much, or you do something because the problem is the Hilbert space formulation has this very delicate connection to empirical measurement probabilities. You have to go through a sequence of steps and through the Born rule, and you get probabilities out. And if you just say, I'm just going to take a hatchet to the axioms, the Hilbert space, the Dirac-von Neumann axioms, just play around with them, you get almost immediately nonsense, right? You get probabilities that don't add up to one, or negative stuff that doesn't make any sense, because you're risking damaging this very delicate bridge or link to probability theory. If you start from a different axiomatic place, arguably simpler and fewer axioms that are more straightforward to explain to the newcomer, that are phrased in old-fashioned probability theory, there's no longer a link you need to get to probability theory. And you could imagine generalizing the theory in ways that would have been difficult to imagine starting from the Hilbert space formulation. And I agree very much with the spirit of what you were doing in that paper. I believe in it. One advantage to reformulating a theory in terms of different axioms, especially axioms that are less abstract and fewer in number and a little less delicate, with less delicate connections to things like probability theory, is that we have greater flexibility to consider varying them and constructing more general theories. And I think that's an interesting thing to do. If you're a student watching this and wondering, maybe I'll work on some interesting project. What can I do? Here's an interesting thing to do. How can we generalize starting from this new starting place?
I was about to ask you. I mean, can you make good on that idea? I mean, yes, I can imagine it, but can you, starting from stochastic dynamics, give me any example of something that looks like quantum mechanics but is not quantum mechanics?
Yes.
Okay.
Here's one example. I'll give you a couple. But
tell me.
Yeah, one example is these sparse conditional probabilities. Are only conditioned on one time, right? They're conditioned on one time, one of these division times.
Yeah.
One generalization would be, is there a theory in which we can condition on 2 times? Is there a theory in which we can condition on 3 or more times? These are now describing theories that where it's not clear the stochastic quantum correspondence works the same way. You don't necessarily get the standard Hilbert space picture. Now, arguably, you can do tricks. there's all these like tricks where you can take a non-Markovian model with conditioning on multiple times and write it in some bigger way. So it's possible that there's some way to write this still in the usual Hilbert space formulation, but you might not.
So you're just putting this out as an open question.
Yeah, open question.
Okay.
This is the thing people work on.
Fine.
And there are a lot of these open questions, right?
Yeah.
That you could, I wouldn't even know how to have asked this question in the Hilbert space point of view, right? So that's one example. I want to make a couple of quick other notes from what you said. So one is this question about should the theory be phrased in terms of things that are more objective? Should we have ingredients that we can't know what they are? There's this long running question about the role and place of unobservables in a physical theory. Should a physical theory contain unobservable things? And I know you don't subscribe to crass operationalism here, which is the statement that, the only things that are physically meaningful, right, are the things that we can have some procedure or operation to go and implement or measure or work with. All of our physical theories at some place or other contain unobservables that play some important role.
And I would like to believe that the moon is there even when I'm not.
Right. Yeah, I would also, and it would be nice to have a justification for believing that, even if, because again, from Dirac von Neumann, it's ambiguous, but the moon is there, which is like a problem.
On the other hand, the global phase of the wave function of the universe, if I have an account where it's not there, then I'm not sorry to see it go, right?
Yeah, but Scott,
it
it's
wasn't
worse.
Observable, even in principle.
But Scott, it's worse. It's worse than that. So now I know that if I were to ask you this, you'd probably not commit to this, but there are a lot of people who are committed to the idea that the objects in the Hilbert space picture, wave functions, maybe apart from global phase, and these sorts of ingredients are like physical things in some sense, that we should ascribe some notion of physicality or ontology to them. But the problem is there's actually this larger set of gauge transformations in quantum mechanics that actually, as far as I can tell, only goes back to 1999 in a philosophy paper by Harvey Brown. He's at University of Oxford. It's called Aspects of Objectivity in Quantum Mechanics, and Kurt, you can link to it because he does this on the very first page.
Sure.
He's a philosopher, and he identifies on the first page a large set of gauge transformations that hold for all quantum systems. You can think of these gauge transformations as a generalization of a unitary change of basis. These are gauge transformations in which you're changing the basis differently at different times. So in the differential geometric language, which maybe not everybody watching this will be familiar with, but some of you may know, you can think of a quantum mechanical system evolving in time as a bunch of Hilbert spaces strung together, like, when you're stringing together, popcorn on a string or something like that, right? Each Hilbert space is a fiber stuck to this string, and this string is time. We call it a 0 plus 1 dimensional manifold. It's just time. And there's a Hilbert space stuck to all the strings, and we can imagine doing an independent unitary rotation on each of the different Hilbert spaces. And this corresponds in somewhat more conventional language to doing what's called a time-dependent unitary transformation. We act with a completely arbitrary time-dependent unitary transformation on the quantum system. And you might go, well, but that doesn't keep things invariant in quantum mechanics. What are you talking about? But it actually turns out that it does. So you can look at the beginning of this paper. As long as all of your self-adjoint operators that represent observables transform in a particular way, just a so-called similarity transformation under the unitary, and the Hamiltonian transforms as what's called a flat gauge connection. And again, this is all actually written out in Harvey's paper, although he doesn't use all this terminology, but that's what it is. Anyone who works on non-abelian gauge theories would immediately see that the Hamiltonian transforms in this very characteristic way. The theory is exactly invariant. Now, what's weird about this, and I know this is getting very technical, but this is a technical objection to try to take Hilbert space objects seriously, is that it means that state vectors can be infinitely remapped however you want, and any trajectory in a Hilbert space that you thought was encoding some kind of invariant information about the system can be mapped to literally any other trajectory by these time-dependent unitaries.
Well,
and
it's clear that we can't reify the actual numbers, in some particular representation, which is tied to our choice of basis and so forth. But I don't take many Worlder, for example, or anyone who believed in the reality of the wave function to be saying anything quite that naive.
Right. Well, but it's tricky then, because then you have to get into the details of exactly what's being proposed. So when I talk to some of the
Okay.
Kurt, I'm sorry, Kurt, you wanted to
Yeah.
Let me make this simpler for everyone.
Yeah.
So, Jacob, you're in the showroom. You came here with some clunker car that you want to trade in. Okay. And you're looking at the options, and someone's coming up to you. His name is Jacob, and he's this
also Jacob. Okay, yeah, got it.
sexy gentleman with this great shirt. And you're like, I'm not just going to be wooed by your smile, Jacob. So, okay, let me hear about the benefits. And then Jacob's trying to sell you. And I also want the audience to not take anything away from if Scott, you don't end up buying from Jacob by the end of this podcast. I mean, that'd be foolish. Most people have to look at a car or whatever 7 times before they make a purchase.
Yeah. No, I mean, look, I've already decided I'm not buying. At this point, I'm happy. I'm happy to chit chat some more. But
okay, the point is that there are 2 ways to go about selling. One is to talk about your own benefits, so Jacob, of your car. The other is to talk about the detriments of the opponents. So, Scott, you have come in with a car. You've also said you're not an instrumentalist. You're not just caring about going from point A to B. You want to know what's going on under the hood.
yes.
So Jacob is saying that, okay, whichever car, all the other cars here will give you some accounts as to what's going on under the hood. Some actually won't, but the ones that you're interested will give an account. They're giving a false account, or an account that when you look actually under the hood, it disappears into dust. So firstly, Scott, what is the car that you're going to drive away from here? What is it that you're committed to, so that Jacob can then say, okay, well, let me compare my approach to that directly.
I should actually say I stopped driving years ago. I didn't like it. I walk or I take Ubers. My wife is a good driver, right? So it's all it's different cars on different days, right? And it's similar in quantum mechanics, I would say, right? I mean, I know how to think like a many worlder. And if you wanted me to like have an ontology that would just you know that was as simple as possible, then I would say, it's going to look like a wave function that is evolving by unitary transformation. And the hard part, of course, is how do I get out of that, my subjective experience, right? Which is related to how do I get probabilities, out of this deterministic picture. But at that point, I feel like that's going to be entangled with, entangled.
no pun intended.
With,
Yes.
yeah, with like enormous questions about what is an observer, what is experience, what is consciousness, right? And these were incredibly confusing questions long before quantum mechanics even came on the picture, right? These, Democritus, asked about these things in 400 BC. That's why I called my book "Quantum Computing Since Democritus." Right, and so I feel like if you take consciousness out of the picture, if you took our own observerhood out of it, and just you just wanted a picture of laws of physics evolving, in which you would have things that looked like observers arising, not necessarily us, but you would have stars, planets, life forms, organisms that would argue about these things and publish papers about them, right? Then you can get all of that, as far as I know, just from the Schrodinger equation, from unitary evolution. Right. But then if you further want to account for sort of our own experience as, being inside the system, then I would say, that was a great mystery even before quantum mechanics, the mind body problem, or, things like that. Quantum mechanics sort of adds a new twist to that problem, adds a new dimension to it, without quite resolving it, right? And then if you wanted to be an instrumentalist, if you wanted to just say, or rather, not deny the reality of anything else, but just say, what is knowable is just what we can observe in principle, and everything else is speculation. Then you go all the way back to what Bohr and Heisenberg were saying in the 1920s, right? To the Copenhagen point of view. Or I like like to say, for me, Copenhagen is basically just shut up and calculate, except without the shutting up part. It's just, endless philosophizing about, why you shouldn't ask, these other questions. And of course that's unsatisfactory to not be able to ask these questions. But we've seen in this conversation that even within Jacob's view, right? Even in this new view, when I ask what are the trajectories of the particles, I am not able to ask that of his theory and get an answer to that. So there always seems to be this sort of thing that I'm, either not allowed to ask, or, maybe I'm allowed to ask, but I don't get an answer from the theory. So I guess that's what I'm driving home in,
All right, so let me just say a couple things about this. So
yeah.
the first is people who are watching this should read this just fabulous paper that Scott wrote in 2013. I think it was called "The Ghost in the Quantum Turing Machine."
Yes.
Right.
Like, if you want
It's a
to
beautiful
read
paper.
something by someone who I guess doesn't call himself officially a philosopher, but is one of the most interesting philosophical things that you've ever read, you should read this. Scott,
Thank
when
you.
we used to run a philosophy of science
Yes.
club at Harvard, and we
Mhm.
invited Scott to come and talk, and it was just fantastic. I mean,
Thanks.
it's so full of interesting ideas, and like everyone should. It's great. I think you wrote that like post tenure, right? Wasn't that your like?
Yeah, it was like immediately post tenure.
Right. It was
Yes.
great. So, like, to be clear, people should know Scott takes this stuff really seriously. He's not like one of these people who's like, philosophy is a waste of time. I don't care about the mind body problem. Like, I'm really glad to be having this conversation with Scott about all this. Okay, so let me now say a couple of quick things. One is, I really like at the end how you like corrected yourself. You said, well, there are things I'm not allowed to ask, but actually, maybe in your approach you're allowed to ask it, but the theory just doesn't supply you with it. I think that's a substantive difference. So in Copenhagen, you're explicitly not supposed to ask certain things. And when you go into a physics seminar, you have to learn pretty early on, there's certain questions you're just not supposed to ask. If you ask them, people will groan and roll their eyes. That's not a very intellectually like vital attitude to have in an academic environment. If you want to ask about the trajectories, you're welcome to. If you want to think, are there trajectories? I'll say, yeah. If you're like, well, is there some way that I can infer or deduce exactly what the trajectories are without doing measurements in the system? I would say, well, the theory doesn't supply you the ability to do that. But of course, there are unobservable features in every formulation of quantum mechanics. I mean, one of the weirdest things about many worlds is that there are all these parallel universes that are filled with people, billions and billions of people in them. And not only have we never been able to do an experiment that directly confirms their existence, but their own interpretation says we can't because they exist only when they fully decohered from our branches, and then there's no way ever to be able to test them. There's this grand conspiracy where the vast, vast majority of the ontology in the universe is completely and forever out of our ability ever to
I wouldn't
directly
call it a
experience.
conspiracy because the theory itself explains why we can't communicate with the
Sure,
other.
sure. I mean, yes,
It's just the linearity of quantum mechanics.
It's just the linearity of quantum mechanics, right? But
A conspiracy would be if we had to contrive it specially so that we couldn't communicate with it.
That's right. We don't have to contrive it
Yeah, yeah.
specially. That's
Yeah.
correct.
Yeah.
Any more than I would have to contrive it specially that you can't like know what the trajectories are going to be without doing the measurements. But I'll tell you, I would rather have microscopic systems sometimes engaging trajectories that we can't specify as our thing that we can't know unless we do a measurement on them, rather than an infinitude of parallel universes containing in each one billions or trillions of sentient beings that we have maybe you prefer the many worlds ontology, although there are some problems with that. But I would certainly say this is certainly no worse than that. Okay, now let me now get to the most substantive of the points that Scott mentioned. So Scott, you said, well, look, I can get all these things out of the Schrodinger equation, out of the wave function in the Schrodinger equation. So now I'm going to turn this back to you. What are you saying that we can get just out of the wave function in the Schrodinger equation?
I am saying that if I program my computer to simulate, a bunch of quantum fields, right? Interacting, according to, let's say the standard model or something like that. Okay, well, first of all, I couldn't actually do this because I would run out of time on my computer. This is why so many people want to build quantum computers. This is one reason why. But in principle, I could do this, right? Run a simulation that would maintain this gigantic evolving wave function. I'm saying that, one could then go inside of that wave function and one could find branches in it that one could interpret as containing things, containing excitations that look a lot like observers, that look a
That's
lot like us.
conjectural, to be
That's
clear.
conjectural.
There's
That's
no
conjectural, but it's only.
proof that
but
you
it's
get a unique set of decoherent branches out of many worlds, right? That's one of
Okay,
the
okay,
outstanding
okay.
questions,
But I would
right?
say it is only conjectural in the same sense that it's conjectural that, if you ran the equations of classical physics, from the beginning of time, then eventually you could get planets and life and all these things. And, we believe that in some sense because, we have the example of our universe where it seems to have happened, right? We can't actually run a computer simulation where we see all of this happen. From the very beginning. But this comes down to, does one believe at all in, scientific materialism, right? Or does one believe that there is, there had to be some external, intelligent designer to guide things along and make and cause the life and intelligence to happen, right? If one doesn't believe that, then one believes that yes, those kinds of things can arise from just mindlessly iterating these equations over and over, and I see no basic change if the equations are quantum mechanical. Then they're just saying that what's going to be evolving is this giant superposition, but within that superposition, I can again find things that look like planets with primordial soup, out of which life will evolve. So I would say, this is why I say that, if we're willing to leave ourselves out of it, which, maybe we shouldn't be, right? But if we don't care about, accounting for our own experience, then, I think Everett actually gives you a very nice picture of what's going on, of how, you can just start with this very simple wave function, let it evolve according to the Schrodinger equation, and then you get, what looks like the thing that you need.
So let me come back to this because I think this is kind of a
Mhm.
central point, right?
Yeah.
So let me put aside the question over whether you get a unique basis in which decoherence singles things out. That again is not known at this point. Certainly not for a theory as complicated as standard model. But I'll tell you is this: if I propose a theory in which let's forget forget all this stuff. Let's suppose I propose.
If the decoherence doesn't happen, then I would say that is not only a problem for many worlds.
Sure,
That is
sure,
a
sure, sure.
problem for any no collapse view of quantum mechanics.
Not no not
Equally.
not nec- not necessarily. For example, if we lived in a universe in which just as throwing this out, a universe in which Bohm mechanics works, you don't have to worry about whether there are different bases in which decoherence works. Bohm mechanics just picks out one particular picture. Okay, but put that aside. Here's what I'll ask: forget about quantum mechanics for a second. Forget about all of our physical theories. Let's do a Library of Babel version of the universe. So maybe people are familiar with this fictional idea of the Library of Babel. This is not the exact version of the story. It's going to be the version that I'm gonna use. Okay, there's a vast library, and you enter the library, and what you see is all the books, right? That begin with what was it? You see a bunch of doors. I'm sorry, a bunch of doors labeled by different letters. You go through the letter T, the door labeled T, and then inside is every single book that could possibly exist that begins with letter T. And then what you do is you go through the door labeled H, and if you go to that door, there's every single book that begins with the letters TH. And this way, you can just sort of find your way. You can write or find every book that could ever be written by just going through a sequence of doors, and this library contains all of them. And someone says, this gives an account of the universe. I mean, after all, we just look at the entire library, and somewhere in there is going to be a universe that looks like ours. But you look at that and go, that's completely vacuous. That doesn't contain any interesting information, right? What we want is a theory that in some way has says some constraints about what kinds of universes are going to happen and which aren't. And two of the problems of the many worlds approach is that it contains so many different kinds of universes that are so radically different. And one of the when you read about people who write about the many worlds interpretation, I mean, in the last podcast I did with you, Kurt, I had this long explanation of the problems of the many worlds approach. But But one problem that I didn't mention in that conversation, but that comes up in the literature, is people don't take it seriously enough. So when Bryce DeWitt in 1970 published his article in Physics Today, this is 13 years after Everett's PhD thesis in 57, announcing and broadcasting what Bryce DeWitt called the many worlds interpretation to the wider physics community. I believe the article was called Quantum Mechanics and Reality. It was in Physics Today. He talks about how there are branches that are sort of reasonable looking in some sense, and there are also these branches that are kind of at the edges of this probability, the tails of the probability distribution that are weird, and weird things happen in them. I don't remember if in that article he introduces the term maverick branches for those, but eventually these became known as maverick branches. But when you read the literature in many worlds, people who, and now I'm going to get kind of technical, people to use what's called Dutch book reasoning to argue how you can get probabilities out, they still stay within these sort of narrow confines of ordinary looking branches and maybe maverick branches. But if you take the many worlds picture seriously, you have to consider branches that are even more bizarre than the branches that conform to whatever game is being played. I call these super maverick branches. They're just maverick branches, but they're branches in which whatever rules you're trying to set up for the game you want to play and use the branches to explain, they're branches in which the rules don't apply because something totally zany happens. And once you include all the super maverick branches, you're basically in the Library of Babel situation where you're explaining everything and you're not putting constraints on which kinds of worlds we expect to see. And there aren't the resources in the many worlds interpretation to narrow down to worlds that at least look somewhat like the ones we see among all the possibilities. That's a major problem.
So certainly I agree that if a theory doesn't rule anything out, if it doesn't tell us that anything is impossible or at least, vanishingly unlikely, then it's vacuous, right? Then it's not doing anything for us, right? And this is why this is part of why I have never been a hardcore many worlder. Right. I will use it pedagogically when it is useful for me. One example of where I found it, indispensable is when I am teaching quantum computing. Right. And I need to explain how, it is possible to take a qubit, do what we call a C NOT gate, a controlled NOT gate, right? Write the result of the qubit somewhere else, sort of copy its state to a different qubit, and now the effect on the first qubit is exactly as if someone had measured it. Right, it is decohered from the perspective of someone who now looks only at the first qubit. Right, and students get incredibly confused about that. They're like, why is that? Right, they feel like it's still a superposition. Right, and like the one explanation that I can give them that seems to click, that seems to work, is to say, look, you might as well say, if you wanted, that the qubit was measured, and just that it was measured by the other qubit. The other qubit did the measurement, and you might as well say that when you measure, right? What does that mean when you measure? It's just that there's a giant C NOT gate that is happening from that qubit to you, to the possible states of your brain, of your measuring device, of your environment, right? To me, that is the core of what, Everettianism is saying. It is sort of the best way to explain that, right? And it is true that I am ultimately not satisfied by a theory that doesn't account for my experience of the world, right? Because, as Democritus said in that famous dialogue, in 400 BC, how can you, ignore the senses when it's from the senses that you get your evidence, right? How can we ignore our own experience when our experience is the only reason why we believe quantum mechanics in the first place, right? So I would say that, with some, I think, fairly, reasonable sounding additional assumptions about, what observers are, how, observers connect to the physical world. Yeah, I can get something that looks like the standard quantum mechanical predictions, out of the Everettian picture, but it is not automatic. I agree that it's not automatic. I don't believe any of the, so-called derivations of the Born rule, of the probabilities from many worlds, for neither Everett's original derivation nor any of the later ones. I feel like, they all sneak in some additional assumption. But I would also say that that's not just a problem for many worlds. I would say that, in any account of quantum mechanics, at some point you're going to have this problem. Where did the Born rule come from, right? Where did probabilities come from? If you didn't want to have probabilities in your fundamental picture. Of course, Jacob, in your account, you do have probabilities
Yes, you do,
in
right?
your fundamental picture, right?
Yeah.
But, if you have an initially deterministic picture, then you're always going to have that problem. So,
Yeah.
So
So it's a good reason not to have a deterministic picture. I mean, it's like
I agree that there are pluses and minuses to all the different major interpretations. Then there are other ones where I only see minuses. We don't have to talk about those maybe, but that's why I don't own a car. I just take Ubers if you like. I just drive different cars as the need arises. I could imagine some future circumstance when, I would want to use Jacob's car, right? I could imagine, if it helps with quantum gravity.
Scott, you can
if
borrow
it
my
helps.
car whenever you want.
Oh, thank you. Thank you. That's so kind of you. Look, if it helps with, understanding a quantum algorithm, I am ready to, take a ride in whichever car will get me to where I'm going. Right now I don't see where, what this car is going to get me, where I couldn't already get. But, I like to keep an open mind.
Let me say a couple of quick things just to follow up about that.
Yeah. Okay.
So, this is one of the annoying places where I'm going to be the annoying philosopher. I'm sorry, but one of the things that philosophers like to do is take a claim, an idea, and really drill down on it and make sure that it really works when you follow it to all of its sort of logical conclusions. When you said, well, if I just have the Schrodinger equation and it's just evolving its wave function and that's going to be good enough, you'll notice that quickly we ran into problems as I was probing that, because I asked you, how do we exactly do this? And you're like, well, kind of like this. And then I pointed out this problem with all these weird branches and we're saying too much. And then you're like, well, we add a few more assumptions and so forth. One of the selling points of the many worlds approach is that it is so simple. I mean, just take the Schrodinger equation and unitary evolution and maybe one or two more things. I have a book on my desk. It's you can sort of see it. It's sitting there right in front of my Einstein doll. It's called Stone Soup. And I think this gives a fantastic metaphor for what happens in an approach like the many worlds interpretation. So those of you who don't know the Stone Soup folktale, these soldiers arrive at a very skeptical town and claim that they can make a delicious, hearty soup out of just water and stones. And the townspeople are amazed by this, and they give them a pot and they start boiling the water. And as they're making the boiling the water, they're like, this is already great, but it'd be even better if we have a little bit of seasoning. And so the townspeople come, they add some seasoning, and they're like, oh, this is already almost perfect, but it'd be even better with a little bit of vegetables. And then the townspeople vegetables. And then by the end, they have this, obviously they've added vegetables and seasoning and meat and broth and all kinds of things. And the townspeople are eating it. And then there's this line in some tellings of the story where one amazed townsperson who wasn't sort of paying attention says, gosh, all this from just water and stones. The many worlds interpretation.
So Jacob, in your account, the equation for the trajectories would be the meat and the vegetables that need to be added.
But I'm very clear up front, right? I'm telling you exactly what the ingredients are. We're not going through and we're, and I say this in the podcast with Kurt, right? To get many worlds off the ground, at least to attempt to get it off the ground, you have to add more and more of these postulates. And I think, I don't know, Scott, how much of the literature you've read on many worlds, but like the number of additional assumptions you need to add is quite large. And a lot of them are very esoteric, metaphysical, very difficult to imagine how we would ever verify that they in fact work. So I call this the Stone Soup problem, and I think it's actually a pretty serious problem with the many worlds approach. But fundamentally, I don't believe it can work. And Scott, you noted this. You said that the derivations of the Born rule out of the many worlds approach, you don't believe any of them. And I agree with you. And I laid out my reasons for skepticism in the podcast I did interview with Kurt recently. But I actually think it's worse than that. Because you might say is, well, maybe we can't derive probability or derive the Born rule. So let's just let's just agree that it's going to be an extra axiom that we add, right? Because this is one route that I know some people take. They're just like, well, if I can't derive probability ab initio without probabilistic assumptions, let's just do many worlds and then we'll see all these universes and we'll somehow attach probabilities to them, say that some are likely, some are unlikely.
There are extremely strong arguments that if you are going to assign probabilities to the branches at all, then any rule for doing that other than the Born rule is going to lead you into nonsense.
Yeah, and these arguments, by the way, show up in Everett's original dissertation, right? Even in the shorter version of his dissertation, the one that was published.
There are many different arguments that all lead to that same conclusion.
There are many different arguments.
Yeah.
But here's the problem. Okay, so if your view was that the branches were fundamental things, that is, they're like the branches themselves are part of are considered fundamental ingredients, then it is completely fine in an axiomatic theory to assign them in the axioms things like probabilities. And this is, for example, what happens in stochastic versions of Bohmian mechanics or what happens in stochastic collapse theories or whatever, right? I mean, if you're taking certain things to be part of your fundamental ingredients, you're allowed to assign them features in your fundamental ingredients. The problem is that in order to get around this preferred basis problem of the many worlds approach, that there's infinitely many bases we could use and what singles out one basis over the other, the idea is that we rely on this the dynamical decoherence process for macro worlds to sort of pick out these approximate macroscopic worlds. The problem is that if your branches are only showing up in an approximate way in later stages of the development of the theory, you can't assign them axiomatic features like probabilities in the axioms. It would be like taking a theory of chemistry, saying I've got an axiomatic theory of chemistry, in which in some situations you end up with tables and chairs, and I'm going to assign properties to the tables and chairs in my axioms of chemistry. Like, you can't do that. The axioms have to apply to the fundamental ingredients.
What people like Deutsch and Wallace try to do then is they say, well, look, we have observers within the many worlds context. They should act as if the probabilities are the Born probabilities. This is what rational decision theory means in that context. And this is then what we mean by probabilities in that context. Right. So I agree that you have to give
that doesn't work.
The probability. Well,
it doesn't work. I mean, and I talked in my podcast with Kurt. I don't know if I want to rehash all those arguments.
Yeah.
But those arguments are all logically circular, right? Because you can't just say, well, I mean, because you use the word should. You should be a rational observer. I don't know what should means. In the many worlds universe, there are just zillions of uncountably many parallel worlds with uncountably many copies of observers in them who do all kinds of things.
All of these arguments are, have to, have some starting point, right? Like I agree that none of them can get, something out of nothing.
But you can't derive probability from them.
None of them can get soup from purely a stone. Okay.
Exactly.
But
right.
To be fair, there is enormous precedent in the history of physics for, making the fundamental ingredients of your theory, as simple as possible, even, like impossibly simple, just atoms in the void, right?
Agreed.
Just, a bunch of particles undergoing. So, and then someone might say, okay, but this doesn't work because you don't have tables and chairs and trees in your fundamental ontology. And you say like, no, that's a misunderstanding. We don't actually need that at all. All of that is derivable. All of that is to be explained from these very simple building blocks, right? I mean, that is, I think that's the goal. Now, I agree that to explain the experience of an observer, it seems like something is missing. There's some additional ingredient that's missing. And maybe. I feel like, speaking of going around in circles, and maybe we are at this point, but I think one place where you and I strongly agree is that saying that you can ask this question and it just I can't give you an answer, or no answer is presently knowable. That is an improvement over saying you're not allowed to ask.
Good. Yes. Let me quickly just go back, because I think there may have been I'm not sure it was a misunderstanding or if it was just you were going a different way, but you said the theory doesn't have to specify chairs as fundamental ingredients. I agree.
Yeah.
I also agree that the axioms should be simple. I completely agree with that.
Yeah. So the Everettians would say you don't have to specify branches as a fundamental ingredient. They would say that branches are like tables and chairs.
Right. But here's the problem, right? You have this fork that's a serious problem for the many worlds approach. If the branches are fundamental, then we can assign probabilities to them in the axioms.
Yeah.
But then you run into all these secondary problems about the preferred basis and so forth. If you make the branches not fundamental, then you can't put axiomatic probabilities in for them because they're not fundamental objects. I'm not saying that the branches can't be emergent. Of course, the chairs, tables can be emergent, but then you can't specify the features of like probabilities of those non-fundamental things in the fundamental axioms. You're kind of stuck between, you either give them axiomatic probabilities, but then they have to be fundamental, like to be things you can specify in the axioms, or they're emergent approximations, and then the axioms can't touch them, can't assign them probabilities. And that's why people aren't making all these decision theoretic rationality arguments for probabilities just for fun. They're doing it because they no longer have the ability to put the probabilities in the axioms anymore. So they have to get them somewhere else, but you just can't. And for all the reasons that you and I agree on. So I don't see this as just an annoying property of the many worlds approach. I'm actually arguing the stone soup problem is the best possibility. Like, I don't think it even survives as stone soup. I think that once they try to add all these ingredients, they show the townspeople, and the townspeople go, that's not soup. It didn't work, right? So I actually think it's actually a pretty serious problem, and it means the many worlds approach, I've not seen any viable version of the many worlds approach that gets around these problems. And that's why if it's just off the table, if we drill down and find that it doesn't work. So look, Scott, if you're coming into this car dealership and you're like, I'm here for the car dealership because my friend Kurt brought me.
But I walk.
But I don't really drive a car. Well, then I don't know that the car dealership is really going to ever work. We really have to bring in someone who actually wants a car. And that's fine. I mean, but certainly what you can't say is all these other cars are just fine. If they were, I would have glommed onto one of these other cars. Yeah.
Look,
Yeah.
to switch metaphors, I mean, I could listen to someone, explain all the severe, enormous, crippling problems with democracy and, agree with that person, right? And it still doesn't mean that I am sold on, monarchism or communism or some other system, right? It's still that's just not enough to make the sale for me, right? There's this saying of, like this system is the worst apart from all the others, right? And I feel like we actually know very well, how to use quantum mechanics in situations where decoherence is strong. Right?
Agreed.
So you could say once there are lots of records of something, all over the place. Once the information about whether this qubit is a 0 or a 1 has spread into the environment, into the air, into the radiation that is flying away from us at the speed of light, then most of us can agree that there is something real there. Right. I think
this is just Zurich's ion selection, quantum Darwinism.
Even a lot of the
approach,
people who call themselves Copenhagenists or instrumentalists would agree at that point that this is real. Like this is now really, this is a real element of reality, even if no one is thinking about it or no one knows about it. It is really there. Right. The whole difficulty is what about when you're not in that situation, right? When you have branches that can interfere with each other in the standard picture, when you have indivisible stochastic dynamics according to your picture, right? And then we don't know, how to say what is real, right? You are sort of asserting that there is a basis in which something real is happening, but then you can't really tell me what, in the sense of giving me trajectories. And, I'm not sure that that's a sufficient improvement over, what I could have said before I learned this, which is, something real is presumably happening there, and I can't tell you what, other than to just write down these equations, write down the wave function, by which I could calculate the probabilities for the different things that I'll see when I look.
Scott, why is supplying trajectories to you so important? You should know Jacob has been on the podcast 4 times, going into technical depth in his theory, as well as dispelling quantum myths. Scott has also been on dispelling quantum myths as well, but also talking about consciousness and AI 3 times here, once with David Chalmers and twice solo. Links in the description.
Well, because in order to improve over the standard quantum mechanics perspective, right? If I just want to say that, there's this wave function, that gives me probabilities, I already knew how to do that, right? I didn't need Jacob's picture for that, right? If I want to sort of make a stronger ontological claim, right? That there are, the photon really goes through one slit, or it really goes through the other slit, even when I'm not looking. Well, then, okay, now I want to know more. I want to know, you ought to be able to give me an equation for this photon, then, right? At least tell me, given that the photon was going through this slit at this time, then what is the probability that it's, at this other place at this other time, right? If you don't know that, then you haven't really told me something about the photon. I wouldn't say that improves on what I already knew about it from standard quantum mechanics.
So let me say a couple of things about all this. The first is this set of statements about, well, when records, which are kind of hard to define, are in the environment far enough, and there are enough of them, and they're far enough away, and they're traveling at the speed, then we all agree. All I'm saying is that in a good physical theory, like I said, I teach general relativity. I teach Jackson electromagnetism, right? I mean, these are theories in which I can be more precise. And when we say that, then stuff just gets far enough out, or enough records, or something like that, I mentioned, Zurich's quantum Darwinism approach, right, ion selection, that sort of thing, that at some point, somewhere, we wave our hand, and then it's like I'm just trying to make us honest and precise about this, right? I think that precision is possible. If the precision is not possible, if it's not possible to make quantum mechanics more precise about this, if it's not possible to eliminate this very severe vagueness, that's interesting. It would be interesting if it were really not possible. If it is possible to reduce it in some axiomatic formulation or interpretation or what have you, that's also interesting, right? And I think that's worth investigating, even if not everybody feels it's necessary. Now, let me say additional things. So far be it for me, who did my PhD in topics that were in or very close to adjacent to string theory, to make an only game in town argument that this is the only game in town. But what I would just say is, I gave a list of criteria for what I thought a reasonable, viable interpretive framework should be. Empirical adequacy, lack of vagueness, unambiguous predictions, at least a schematic picture of the classical limit, not an endless list of speculative metaphysical hypotheses. Like, these are just bare minimum requirements we would put on a theory. I didn't even add Occam's razor, but you could add that too. All these things you could further add. My argument is that none of our approaches meet that minimum set of requirements. If they did, I would have become. I did spend various points of my career here working in various other interpretive frameworks. Like I said, I spent a long time in the modal interpretations, which Scott will remember when I had said lots of strange things of modal interpretations many years ago. I arrived here because this met those requirements and the others didn't. Now, it doesn't do everything you might like. There are aesthetic criteria you might further want. You might want to be able to say what's going on in every circumstance, what exactly are the trajectories the system is taking.
I think the whole reason why there's an interpretation debate is that for every interpretation, you can state like an obvious sounding condition that interpretation fails to satisfy, right? In the case of yours, that condition would be that, for every element that the theory posits as being real, you have to give an equation that says how that element evolves in time.
But we don't make that
if it's really fundamental.
But Scott, the reason I think that's aesthetic is because we don't hold any of our other physical theories to that standard. All of our other physical theories contain things where we don't have an ability to describe them. We don't know what equations to apply to them. If you take general relativity as a great example of this, right? We have access, if you think of space-time as a four-dimensional manifold, we have access to an incredibly thin sliver of that entire space-time manifold. Most of space-time is and will forever be completely inaccessible to us. And you can quickly run into situations in which unobservable ingredients of our various physical theories, we can't describe what's going on with them. We can't,
I don't really agree with the analogy. I mean, I would say in GR, you can posit a a space-like slice, once you've posited it, then, you have this, a field equation that tells you how to evolve it forward, right? Except, when you run into singularities or
Or you run into Cauchy horizons, or you run into,
that's right. That's
there's,
right.
yeah,
Or varies.
yeah.
But in many conditions, you can just extend that equation forward, right? If you believe in standard quantum mechanics, you say, once you tell me what is the wave function, you tell me what is the Hamiltonian, then I can just take that psi and map it to e to the minus iht psi. I can, propagate that equation forward, right? In your case, you are telling me that something is real. The positions of these particles in space, or which slit the photon goes through, and you're not giving me an evolution equation for that thing that you have posited as real. Which, okay, like I said, every interpretation has some hole or something that it's failing to satisfy, and that's the one for you. But I don't see that that's necessarily less bad than, let's say, the Everett interpretation not having an answer to where the probabilities come from.
Well, to be clear, I think it's kind of a more serious problem when the entire empirical content of quantum mechanics, which consists of measurement probabilities, can't be obtained from your. I mean, it's one thing to say that certain unobservable features of a theory, that we don't have equations for them, right? It's another thing to say that the observable features of the theory, the empirical content, we can't get, right? I mean,
Well,
that'd be like saying not that we can't make predictions about what's outside of our accessible light cones in general relativity, but we can't make predictions about what's inside of our accessible light cones in
I mean,
general
we could
relativity.
say every interpretation of quantum mechanics has the property that to actually use that interpretation to make, to actually connect it to the experiments that we can do, we need some auxiliary assumption that looks something like, the real world is decoherent. It contains things like records and so forth. So every interpretation is going to have some story of that kind that it tells, where some vagueness will enter.
Right,
It
but
seems
the
to me.
problem, as we mentioned in the many worlds approach, is
Yeah.
that that doesn't appear to be possible in principle. The many worlds approach, like it's much more severe problem. So let me actually just step back and go back to. I'm going to just say, suppose you go back, you rewind the clock back to 1923, 1924, which is right around the time when people like Pauli and Bohr and Heisenberg were beginning to doubt that there could be a physical picture of stuff happening. Because back then, people still thought there were particles going around atoms and stuff, right? That there were fields interacting with particles, that these were all happening in some kind of, there was an actual ontological picture. And people began openly to doubt whether there could be any picture because no one could come up with any laws that, when combined with any such clear picture, could yield the correct empirical predictions of quantum mechanics. And then Heisenberg begins his matrix mechanics paper in 1925, in the spring of 1925, with a bold statement that we should give up these pictures altogether and that we should just do everything in a crass instrumentalist way. And, so people thought that there just were no laws that would work, that there was just no laws you could find. You could tell an alternative history in which the theory of stochastic processes was discovered way earlier than in fact it was. Kolmogorov didn't publish his axiomatization of probability theory in 1933, a year after von Neumann's book on quantum mechanics. He published it in 1833. There's some retrocausal loop, and he goes back and he publishes his axiomatic account of probability theory. Markov doesn't, first introduce the Markov matrix in 1906 in an obscure journal, but this all happens in the 1800s. People develop a robust probabilistic theory of stochastic processes starting in the 1800s. And then people begin exploring non-Markovian processes, and someone mentions, what about indivisibility? And then 1923, 1924 comes along, and they go, well, I mean, we have these indivisible processes. Let's try those laws. They try them, and they get all the correct empirical results. They're able to derive this beautiful mathematical correspondence, the way that we took Newtonian mechanics and derived the Hamiltonian formulation, right? You could do things much more beautifully, more elegantly in this Hamiltonian formulation. I think a lot of the interpretive questions we would have today wouldn't exist, right? The measurement problem wouldn't have
No,
happened.
I don't
Yeah.
agree. If I imagine myself in that alternative history that you have sketched, I'm still asking myself, well, then, what the hell are these indivisible stochastic dynamics, right? What do how is that even dynamics at all, right? What are the transition probabilities? What are the trajectories that these particles are following? And then in your alternative history, if a Schrodinger comes along and says, look, you can think of it, in terms of this wave of amplitudes, right, as Schrodinger came along in our history, then, in that history, just like in this one, I'd say, "Oh, that's nice. That helps me." Right?
As a helpful picture, just like the Hamlet-Jacobi picture is a very
Yeah,
helpful picture,
yeah,
right? But
yeah.
but but it would immediately come along with all of these bizarre mysteries like superposition and the measurement problem. But people would always say, they would say, okay, well, this is a really useful mathematical picture. It gives some visualization. But at the end of the day, if we ever have some question about what happens when you do a measurement, we have this more mechanical picture, just like in the Hamiltonian formulation. If you're living in
This is
phase space land for a while and you
I
get
mean,
confused,
this
yeah.
is always the problem with sort of going back to history, right? The many worlders will also constantly say this. They will say, "Well, look, it's not fair that Copenhagen came first, right? If only people had just accepted many worlds in the 1920s, then Copenhagen would have been this bizarre instrumentalist, deviation from it that would have had to, win acceptance on its own steam and so forth, right? Well, okay, in this branch of the wave function, history happens a certain way, right? And then, if you want to win converts to a new view, then you have to meet them, having learned whatever they've learned from the previous views,
Certainly
and
true.
show them why the new view is an improvement over
Yeah.
what they could already do.
I mean,
Right?
interestingly, Schrodinger did, if you read his fourth
Mhm.
lecture on wave mechanics, what section 15, the
Yeah.
interpretation of the generalized psi function,
Mhm.
he presents an embryonic many worlds picture,
Yes.
right? He
Yes.
actually,
Mhm.
so it's not that people didn't think about these things. If you read
Yeah.
some of the early papers at this
Yep.
time, in the 20s, people did, some of them were
Yep.
imagining this sort of, but they didn't embrace it because it doesn't work. And what happened, it's not that Everett came along and found a way to make it work. Everett found a story he could tell that some people found very compelling, but it still doesn't work. Like the people who gave us quantum mechanics, they were very smart. They didn't have everything. They didn't know that you could write laws in certain ways, but they certainly thought about some of these ideas at the
And
time
I mean, the
and
people who
rejected them.
but Jacob, the people who added more and more epicycles to the Ptolemaic model, they were also very smart, right? They were
Very.
also, trying to get things to work, and they would have said, okay, okay, yeah, maybe, you could imagine, the Earth going around the sun, but that just doesn't work because we don't feel ourselves spinning, right?
Yeah, which we don't. It actually requires a lot of physics to explain why
That's
pendulums
right,
can
that's
feel
right.
Earth's
No, and
rotation, but
and
we can't.
the
Yeah.
Everettians have a whole story in which, Everett is like Copernicus, right? He's just giving a reinterpretation, like, yeah, we don't feel ourselves being in all these different branches, but you wouldn't, if that were what was going on, right?
Well, that's what he said actually in a response to Bryce DeWitt. Because when
Yeah,
Bryce DeWitt, the theoretical
yeah,
physicist who eventually
yeah,
propagated the
that's
theory,
right.
talked to Everett in his letter and said, I don't branch. Everett said,
Yeah,
well, what would it feel like if you did? And he actually
right.
made this Copernican analogy. The problem,
Yeah,
of course, is that the Copernican story says that all humans on Earth, if Earth is in fact turning and going around the sun, then all humans on Earth will see the sun apparently move through this. Like it predicts what all humans will see. The problem with the Everett approach is that it predicts everything. It predicts every like there will be observer copies who see absolutely everything, and then you either run into a circularity of saying, well, the reason we see the world we see is because we're going to condition on us being the ones who see the world. It's a totally circular argument. Or you say something like, well, what would the typical copy of the observer see? But then typicality is a question of what's the most probable. Typicality is a probability statement, and then you run into the circularity of how do you get probability out of the Everett approach. Like all of this stuff just doesn't work, and I think that the early people who had quantum mechanics, realized that at some level that this is just not a thing that ultimately can work without slogans. But look, history ended up turning out a particular way. It's hard to know exactly what would have happened if it had come out a different way. I would argue that if they'd had a physical picture, a simple physical picture, simpler than the Hilbert space Dirac von Neumann axioms with all the exotica that you get from those, they would have viewed the Hilbert space picture just as we view the Hamiltonian phase space picture today, as a very powerful mathematical apparatus that we can use to do all kinds of amazing calculations and simplify things and specify particular kinds of interactions. But that at the end of the day, when you run into any conceptual confusion, you can retreat back to a physical picture. In the Newtonian case, to bodies moving in space, interacting with fields. And in this picture, to objects with configurations with laws that are just more general. Now, I want to ask one more quick thing. You said they would probably say something like, well, what are these laws? What are these conditional probabilities? Like, what are these laws? The question of what laws are is, as Scott, I'm sure you know, a pretty hot topic in metaphysics today, in the metaphysics and philosophy of science.
I don't
What
follow
kinds of things?
metaphysics
Say
enough.
what?
I don't follow enough metaphysics to know that, but okay.
That's okay. Nobody's
All right.
perfect.
All right.
I'm just joking. I'm just joking. But like, what is a law?
Yes.
Like, I mean, I don't know what Newton's law is. I mean, I know what it is as an equation,
Yeah.
but like, I have no greater understanding about what is Newton's, like, what does it mean to say that there's this law that takes the present configuration of a system and the configuration infinitesimally earlier in time, or equivalently, the present configuration of the velocity, and then, like, how is it doing this? And if you talk to people who are Humeans about laws, this is a term that was introduced by David Lewis to refer to a certain view on the metaphysics of laws that in some sense is connected with David Hume, the philosopher's ideas about nature. Then what you'd say is you don't believe in laws at all. Like, because the idea of a law is just so weird and strange, laws are not primal things. They're just tools that humans use to summarize phenomena. And, but the upside of all this is that, yeah, indivisible laws are weird because they're different from the kind of differential in time Markov-style laws that we've been using for the past few hundred years. But that's just an historical contingency. They're no weirder than a Markov law or Newton's second law. They're all weird. All laws are strange. They're just stranger because we're newer to the idea.
Okay, what I'm saying is not that the law is weird. I'm saying in a place where I might have expected there to be a law in your picture, namely for the transition probabilities, there is actually no law at all.
Yes, in some cases there's no law. In your Ghost in the Quantum Turing Machine
Yes.
paper, you introduce a lovely term for unpredictability that is not even probabilistic. You point to this book from the 1920s by this economist, Frank Knight.
Yes.
You call it Knightian uncertainty,
Yes.
right? Circumstances in which we can't even put probabilities on certain things.
Mhm.
And interestingly, this is definitely not unique to quantum mechanics. So here I can put my general relativistic hat on. One of the conjectures about general relativity is just that all reasonable spacetimes it's called global hyperbolicity. They've been globally hyperbolic, which just means that you don't have Cauchy horizons. The equations apply to everything, but this is just a guess, right? There are like solutions to the Einstein field equation where you get Cauchy horizons. These are places where general relativity simply fails to make further predictions about what's going to happen next. And you can't put probabilities on these things. They're not all black hole singularities. There are other situations where you get Cauchy horizons. So like the idea that you could have situations in which the theory doesn't render a prediction about what comes next, that's not a new idea.
Well, look, as you
Yeah.
know well, because you read Ghost in the Quantum Turing Machine, I am very ready to contemplate Knightian uncertainty about the initial conditions.
Right.
Right? Because that is a thing that in our experience, the laws of physics famously leave unspecified. Right? I am much more hesitant to allow Knightian uncertainty in the evolution rules, and that seems to
Okay.
be what you're doing.
Yeah.
All right.
That's fine.
So-
Although I will tell you that even in like standard quantum mechanics, we are unable to assign probability distributions to a variety of things. You can't assign joint probability distributions to incompatible observables, and
I feel like this all sort of boils down to the same issue of just multi-time or transition probabilities.
It all boils down to the basic fact that we're epistemically limited beings. We're trying to do the best we can in a universe that we're a part of, that we're physically embodied in. And we're very fortunate that we have a theory that lets us make as many predictions as we'd like to make, but we can't make all the predictions we would like to make. And yes, that is a bullet I'm definitely going to bite. I'm going to bite that bullet. But I will say that anytime someone comes along with a new picture of reality, it opens up new possible connections to new fields, interdisciplinary connections, new ways of thinking about old problems, and possible new generalizations, maybe new pedagogical teaching techniques. And even arguably opens us up to rethinking certain things that we took for granted. I mean, sometimes, John Bell, and there's the only thing I'll say about John Bell here, John Bell was very clear that sometimes having a physical model can really tell you a lot about things that you thought were true, right? There was this prevailing idea from John von Neumann that hidden variables were just ruled out like completely. And although Bell wasn't the first to notice this, Greta Herrmann noticed it almost immediately in the 1930s. Bell independently rediscovered this, and he rediscovered this flaw in the von Neumann proof because he had a model, Bohmian mechanics, that made clear that there was a problem here. And of course, Bohmian mechanics also helped lead to the development of decoherence, having physical pictures can lead to rethinking things, including even things like the classic theorems, like Bell's theorem and its related theorems. So I think that's also a useful thing. And in my podcast interview with Kurt, we talk about possible connections to rethinking how causation is supposed to work. I think there's a lot of stuff you can do with this, and it's not for everybody. But unless we identify some actual inconsistency, some real problem, either one could say that there is just an inconsistency, something that just doesn't work. Or one can say that this is trivial or uninteresting or isn't useful to me or doesn't do better than the things I already like. And if we're basically arriving at either of those two positions, so if we're not arriving at the inconsistency position, but we're arriving at the position that, well, maybe this doesn't work for me, or I like these other things, or it's trivial, or anyone could have said that or whatever, I'm actually satisfied with that because some people will find that satisfying, others won't, and that's the way the world is.
Right now, I feel about your account the same way that I feel about category theory, let's say, or lambda calculus, right? I have friends who just swear by these things, right? This is the way to understand everything. And they will happily take something that I know how to prove in one paragraph, normally, and they will give a proof using category theory that's 20 pages. And they would say
with lots of diagrams, all these diagrams.
Right, with all these diagrams. And I was like, can't you see that this is so much better, that this is more insightful? And I'm like, okay, I guess for you it is. I guess so, right? Go in peace, carry on. Right? You haven't yet made the sale by showing what this can do for me. But,
right.
I'm open to the possibility that maybe it will in the future. So
that sounds like a wonderful place to close.
Yes.
I'm still waiting for John Bias to tell me what dagger symmetric monoidal categories have to say that is different than just translating something from quantum mechanics and then translating it back. Because usually the insight comes from translating to a different field and then doing something in this other language that you couldn't in the former, then translating back. But as far as I could see, you just translate and then translate back without anything new being generated. So I'm in a similar boat as Scott, and I think you and I have talked about this off air, Jacob.
Yeah, but let me just point this out, right? There are people who don't know quantum mechanics and I feel so sad for those people. They don't know what they're missing. Everyone should learn quantum mechanics. It's such a beautiful theory. But there are people who work in statistics who don't do quantum mechanics, and they've developed all kinds of incredibly interesting and sophisticated ways of thinking about statistics. And there's a barrier between them and people who work in quantum mechanics because quantum mechanics is phrased in this very different language. If you hand them a version of quantum mechanics that's phrased in the language of ordinary probability theory, suddenly certain things that might have been difficult to apply from statistics are suddenly applicable. And this is just so new.
It's a case that I could imagine you making, but I would say that you have not made that case.
I have not. No, right. I agree. This is speculative. Like I said, this is brand new.
Right. And if you want to show that this is actually a better way to introduce quantum mechanics to people who have never seen it before, then you need to show that by showing all the phenomena of quantum mechanics, that you can explain them better, in this way. I don't see that you've done that. But, that is a thing that if you did that, then that would make me want to, come back to look at this car again.
It's rare in science or in philosophy to find oneself with a blank canvas page to be filled in. I view that as super exciting, especially the theory is old and battle-tested as quantum mechanics. So I relish that opportunity. I feel like we've already made a lot of progress, and I'm very excited about the things that hopefully we'll be able to explore going forward.
Well, usually quantum mechanics courses start with either the double slit or the Stern-Gerlach experiment, and then trying to explain that. So, Jacob, I welcome a lecture of an account of the double slit and or Stern-Gerlach, but just without referencing the ordinary Hilbert space picture, just your picture. Mm-hmm. That'd be great.
Well, so I sent you a document, Kurt. That
you already have that in paper form. And so I'll put that on screen. And Scott, it was wonderful to speak with you again. Jacob, thank you so much. This has been so much fun.
This was delightful. And Scott, it's always a pleasure to chat. Hopefully we'll find more opportunities.
Pleasure. talking to you, Jake.
Okay, good to see you all.
Okay. Yeah, good to see you.
I've received several messages, emails, and comments from professors saying that they recommend Theories of Everything to their students, and that's fantastic. If you're a professor or lecturer and there's a particular standout episode that your students can benefit from, please do share. And as always, feel free to contact me. So my question was, you gave an example earlier about the C-Naught gate, and then you
Yes.
used many worlds to explain that. You
Yes.
said that some people find that
Yeah.
easier. Do you have any other examples of situations where students are confused and then you use a different interpretation to explain it?
Not really. I'm not usually, using interpretations to explain conceptual points, right? It's um let me think. I mean, I certainly talk about Bohmian mechanics, like when we talk about, the Bell inequality and the CHSH game, right? But that's partly just for reasons of history to explain, why did Bell care about this in the first place? Right? I haven't yet seen a situation where Bohmian mechanics helps me to explain something that I couldn't have explained without it.
I see. Because
Uh,
earlier you were saying, like, look, you're willing to use an Uber, which is any car to get from point A to B,
yeah,
but it sounds like
yeah.
you'll use an Uber as long as it's a Hummer, as long as it's the same car.
Yeah, usually, when we're trying to solve a concrete problem, like what does this quantum algorithm do? Well, then the whole point, like, we don't need interpretation for that, right? We know how to, what that calculation looks like, right? Interpretation is mostly relevant when we want to include ourselves in the picture, right? And then, yeah.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Kurt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Kurt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, Toll listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/KurtJMungle and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.